What if everything you've ever seen, touched, or experienced, the depth of a star-filled sky, the solidity of the ground beneath your feet, even the passage of time itself, was nothing more than an elaborate illusion? Picture a universe where reality as we know it is not what it seems, where three-dimensional space is just a magnificent projection emerging from a simpler, lower-dimensional realm. This isn't science fiction. It's one of the most daring ideas in modern physics, the holographic principle. It suggests that the rich complexity of our cosmos, from the way black holes behave to the fundamental laws that govern particles, might actually be explained by fewer dimensions. It's a concept that turns our intuition inside out and invites us to question the very nature of existence. Think about that for a moment. We move through a world that feels undeniably real, 3 dimensions of space, one of time. But what if this is all a kind of cosmic trick, a breathtakingly detailed hologram? The idea isn't just wild speculation. It grew from the deepest puzzles in theoretical physics, born from the study of black holes and the paradoxes they present. Scientists began asking, where does information go when it falls into a black hole? How can something so immense be described by laws that seem to operate on a far simpler plane? The answer, some propose, lies in rethinking dimensions altogether. If this is true, it means that everything we perceive could be encoded on a distant, 2-dimensional surface, like a movie projected onto the screen of reality. In this video, we're going to unravel this extraordinary possibility together. We'll journey from the origins of the holographic principle to its staggering implications, how it might finally bridge the gap between gravity and quantum mechanics, how it redefines our understanding of space and time, and how it encourages us to see the universe not as a collection of things, but as information, relationship, and emergence. This is more than a theory, it's a new way of seeing, and by the end of our exploration, you may never look at the world or the cosmos the same way again. So settle in, open your mind, and let's begin where every great idea starts, with a question. To understand how such a radical idea could even emerge, we need to rewind to a scientific conundrum that was keeping physicists up at night: the black hole information paradox. It all started with Stephen Hawking's stunning revelation in the 1970s that black holes aren't completely black. They slowly leak radiation and can eventually evaporate, disappearing entirely. This Hawking radiation posed a terrifying question for physics. What happens to all the information about the stars, gas, or unlucky spacecraft that fell in? The laws of quantum mechanics state that information can never be truly destroyed. It must be preserved in some form. But if a black hole vanishes, it seems to take that information with it, permanently erased from the universe. This wasn't just a minor puzzle. It was a direct contradiction between the two pillars of modern physics, general relativity and quantum mechanics. Enter two brilliant and bold thinkers, Gerard T. Hooft and Leonard Susskind. In the early 1990s, T. Hooft was grappling with this very problem. He made a fascinating connection by looking at the mathematics of a black hole's entropy, which is a measure of its hidden information or disorder. He found something astonishing. The entropy of a black hole, the amount of information it contains, didn't scale with its volume, as you might intuitively expect for a 3-dimensional object. Instead, it scaled with the area of its event horizon, its 2-dimensional surface. This was a huge clue. It suggested that all the information needed to describe everything within the black hole's volume could be perfectly stored on its boundary, its outer shell. It was like realizing the entire contents of a library could be written on the surface of its front door. Hooft, inspired by the way a hologram can encode a three-dimensional image on a two-dimensional flat plate, proposed that the universe itself might operate on this same principle. He suggested that we might be living in a kind of hologram where the true, fundamental laws of physics are written on a distant, two-dimensional surface, and our perception of a three-dimensional world is a magnificent projection. Initially, his colleague Leonard Susskind was deeply skeptical, even calling the idea crazy. But the more Susskind wrestled with it, the more he became convinced that Hooft was onto something profound. Susskind, along with others, expanded the idea, arguing that this wasn't just a quirk of black holes but a fundamental property of space and time itself. Their proposal became known as the holographic principle, a paradigm shift that dared to suggest that the universe is not what it appears to be. This wasn't just a new theory, it was a completely new way of framing reality, born from the most extreme objects in the cosmos and the need to preserve the most fundamental rule of quantum physics. So what exactly are these dimensions we're talking about? We often think of them as the directions we can move in, left and right, forward and backward, up and down. That's our familiar three-dimensional space, but in physics, a dimension is simply a measurable extent of some kind, a degree of freedom. It's a fundamental parameter needed to describe the position and state of anything in the universe. To truly appreciate the holographic principle's radical suggestion that we might need fewer dimensions, we first need a solid grasp of what dimensions are and how physicists play with them. A wonderful way to wrap your head around this is through Edwin Abbott's charming 1884 novella Flatland. Abbott invites us into a world that exists entirely in two dimensions, a flat plane like a sheet of paper. The inhabitants of Flatland are geometric shapes, triangles, squares, circles, all living their lives confined to this flat surface. They can move north, south, east, and west, but the very concept of up or down is unimaginable to them. It's a direction that simply doesn't exist in their reality. Their entire universe and their understanding of physics are built upon just two dimensions. Now, imagine a three-dimensional object like a sphere passing through Flatland. To the Flatlanders, this event would be utterly bewildering. They wouldn't see a sphere. Instead, they would witness a single point that suddenly appears, grows into a circle of increasing size, then shrinks back down to a point before vanishing. Their perception is limited to a two-dimensional cross-section of a much richer, three-dimensional object. This brilliant analogy helps us, the three-dimensional viewers, ponder a startling possibility. Could our own perception be just as limited? Are we, like the Flatlanders, only seeing a slice of a much higher dimensional reality? This idea that there might be more to existence than meets the eye isn't just philosophical fiction. It's a serious proposal in modern theoretical physics, most notably in string theory. String theory is an ambitious framework that attempts to reconcile Einstein's general relativity with quantum mechanics by proposing that the fundamental building blocks of the universe are not point-like particles but incredibly tiny, vibrating strings. The mathematics of string theory, however, only works consistently if the universe has more than the three spatial dimensions we experience. Specifically, most versions require 10 or even 11 dimensions for the equations to balance and make sense. This immediately raises a glaring question. If there are more dimensions, where are they? Why don't we see them? The prevailing explanation is a process called compactification. The extra dimensions are thought to be curled up or folded in upon themselves at an astonishingly small scale, a scale far smaller than anything our most powerful particle colliders can currently probe. Imagine a garden hose. From a distance, it looks like a simple one-dimensional line, but if you get very, very close, you realize it actually has a two-dimensional surface curled into a tiny cylinder. In a similar way, the extra dimensions of string theory could be compactified into intricate, complex shapes at every single point in space, so tiny that they are completely hidden from our everyday perception. Our reality, in this view, is like the surface of the hose appearing simple from our macroscopic viewpoint, but harboring a hidden, compact complexity at the microscopic level. This dance between visible and hidden dimensions sets the stage for the holographic principle's even more dramatic proposal. String theory adds more dimensions to make its math work, but holography does the opposite. It suggests we can describe complex systems by using fewer dimensions. It's a different kind of simplification. While string theory imagines tiny, curled-up dimensions everywhere, the holographic principle posits that the true, fundamental description of a volume of space, with all its gravity and particles, might actually lie on its boundary, a surface with one less dimension. A three-dimensional world could be encoded on a two-dimensional surface. This doesn't mean the extra dimensions are irrelevant. In fact, concepts from string theory, like the famous AD/CFT correspondence, provide some of the most powerful mathematical realizations of the holographic idea. Understanding dimensions from the fictional flat plane to the hyper-dimensional strings of theory is the essential first step in seeing how this incredible dimensional trick could possibly work. So if our universe is a projection, where is this cosmic projector, and what does the screen look like? The holographic principle paints a picture where all the information that makes up our reality, every star, every atom, every law of physics, is not fundamentally located within the three-dimensional space we inhabit. Instead, it is perfectly encoded on a distant, two-dimensional boundary that encloses our observable universe. This isn't a physical screen in the conventional sense, but a mathematical surface where the fundamental degrees of freedom, the ultimate bits of information, reside. In this view, our rich, three-dimensional experience is not the primary reality. It is a kind of magnificent emergent illusion, a translation of that lower dimensional data into the world we perceive. This leads to one of the most profound implications. The very things we consider fundamental might not be fundamental at all. Take gravity, for example. In our standard view, gravity is a force mediated by particles called gravitons, warping the fabric of spacetime itself. But in the holographic universe, gravity might not be a fundamental force. Instead, it could be an emergent phenomenon, a consequence of the way information is entangled and processed on that lower dimensional boundary. It would be analogous to the way the temperature of a gas emerges from the collective, chaotic motion of countless molecules. No single molecule has a temperature, but together they create it. Similarly, the force we experience as gravity could be a collective effect, a story that only makes sense when you have enough information interacting in the right way on the two-dimensional surface. Particles like electrons and quarks might also not be the ultimate building blocks, but rather convenient descriptions for complex patterns encoded on the boundary. This radically transforms our understanding of space and time. We tend to think of space as an empty stage upon which the drama of matter and energy plays out. The holographic principle suggests the stage itself is part of the show, constructed from the information on the boundary. Space and time become emergent properties, a framework that crystallizes from the complex quantum interactions happening on that lower dimensional surface. It's a concept that turns our intuition inside out. The solidity of the world around us, the undeniable feeling of here versus there, of now versus then, could all be a useful and consistent interpretation of a deeper, simpler reality that operates in fewer dimensions. The universe isn't in space and time. Space and time are in the universe, emerging from it. Where does this leave our everyday experience? If this is true, it means the world we interact with is a kind of incredibly detailed and self-consistent simulation, but not one running on a computer in some other reality. It is a natural consequence of the universe's underlying information theoretic nature. The chair you're sitting on feels solid not because it is fundamentally solid in some absolute sense, but because the information that describes it, the position of its atoms, the forces holding them together, is encoded on the boundary and translated into your conscious experience in a way that is perfectly consistent and interactive. Your perception of moving through time is the unfolding of this information in a coherent sequence. This doesn't make our reality any less real to us. The laws of physics still hold, and your experiences are genuine. But it suggests that the ultimate truth of the cosmos is far stranger and more elegant than we ever imagined, with a beautiful simplicity potentially lying just beneath the surface of our complex perceptions. It was the bizarre and extreme nature of black holes that ultimately forced physicists to consider such a radical rethinking of reality. These cosmic anomalies, regions of spacetime where gravity is so intense that not even light can escape, became the unexpected gateway to the holographic principle. They are the universe's ultimate natural laboratories, pushing the laws of physics to their breaking point and revealing clues we couldn't find anywhere else. To understand why, we need to look at two of their most defining features: the event horizon and a concept known as black hole entropy. The event horizon is the point of no return, the invisible boundary surrounding a black hole. Once anything, matter, light, information crosses this threshold, it is irretrievably lost to the outside universe, or so we thought. This one-way street creates a profound puzzle. Then there's the idea of entropy. In thermodynamics, entropy is a measure of disorder or randomness, and it's closely linked to information. The more possible ways a system can be arranged, the higher its entropy. In the 1970s, a young physicist named Jacob Bekenstein made a startling proposal. He argued that a black hole must have entropy, and that this entropy is proportional to the area of its event horizon, not to its volume. This was a huge clue. For any ordinary three-dimensional object like a book or a star, the amount of information it can contain, its entropy, scales with its volume. But a black hole, the most massive object imaginable, seemed to play by different rules. Its information content was dictated by its surface area. It was as if the entire contents of a three-dimensional safe were written on its two-dimensional door. This bizarre finding set the stage for Stephen Hawking's earth-shattering discovery. Hawking applied quantum theory to the space just outside a black hole's event horizon and realized something extraordinary. He found that black holes aren't completely black. Due to quantum fluctuations, they should slowly emit a faint glow of radiation, now famously known as Hawking radiation. This radiation would carry away energy, causing the black hole to gradually lose mass and eventually evaporate completely over astronomical timescales. While this was a monumental achievement, it created a catastrophic problem: the information paradox. Hawking's initial calculations suggested that this radiation was purely thermal, random noise devoid of any information about what fell into the black hole. If a black hole formed from a collapsed star and then evaporated away, radiating only this random heat, all the specific, detailed information about that star, what atoms it was made of, its structure, its history, would be lost forever. This violates a cornerstone principle of quantum mechanics. That information cannot be created or destroyed. It can only be transformed. The universe, it seemed, had a glaring contradiction at its heart. Physics was facing a crisis. This is precisely where the holographic principle entered the scene. not as abstract philosophy, but as a potential solution to a very concrete problem. Gerard T. Hooft and Leonard Susskind saw in Bekenstein's area law entropy a revolutionary hint. They proposed that the information about everything that ever fell into the black hole wasn't lost inside its mysterious interior. Instead, it was never actually there to begin with. The information remains encoded on the event horizon itself, imprinted on its two-dimensional surface. The Hawking radiation, then, isn't random noise. As the black hole evaporates, this process slowly and carefully reads out that encoded information from the horizon, returning it to the universe in the radiation itself. The paradox is resolved, information is preserved. The three-dimensional interior, with all its terrifying mystery, is a projection, while the true story is written on the two-dimensional boundary. This makes black holes the perfect testing ground, however theoretical, for the idea of dimensional reduction. They are cosmic examples where the mathematics forces a description of a three-dimensional volume in terms of a two-dimensional surface. They show us that under the most extreme conditions, our intuitive understanding of space breaks down and a deeper, more holographic reality emerges. The clues they offer point toward a universe where information is the most fundamental currency, and where the dimensions we experience might be the result of a magnificent cosmic translation. But if black holes offer a tantalizing hint of holography, string theory provides the mathematical machinery to build an entire universe upon it. As one of the most ambitious frameworks in physics, string theory proposes a beautiful but bizarre fix to the conflicts between quantum mechanics and gravity. It suggests that the fundamental constituents of reality are not zero-dimensional points but unimaginably tiny, vibrating strings. The way these strings vibrate, their frequency and mode, determines the properties of the particles they become. Much like different vibrations of a violin string produce distinct musical notes. One string vibrating one way might be an electron, while another vibration creates a quark, and yet another manifests as the messenger of light, the photon. For this elegant idea to work mathematically, for the equations to balance and avoid nonsensical infinities, string theory makes an extraordinary demand. The universe must have more than the three spatial dimensions we experience. Most versions require a total of 10 or even 11 dimensions to remain consistent. This immediately presents an obvious and pressing question. If there are extra dimensions, where are they? Why don't we see them or move through them? The answer lies in a process called compactification. Theorists propose that these extra dimensions are not vast and expansive like the three we know. Instead, they are curled up or compactified into an exceedingly tiny, complex shape at every single point in space. To visualize this, think of a long, thin garden hose stretched across a lawn. From a distance, it appears to be a simple one-dimensional line, but if you were an ant crawling on its surface, you would discover it actually has a second dimension, the circular dimension going around its circumference. This dimension is there, but it is compact or curled up, so small that it's hidden from a macroscopic view. In string theory, the 6 or 7 extra dimensions are imagined to be compactified into intricate, multi-dimensional shapes known as Calabi-Yau manifolds. These are complex geometric forms existing at the Planck scale, which is so profoundly small that probing them directly is far beyond our current technological capabilities. So, while string theory adds dimensions to make its math work, they are effectively hidden from our everyday perception, folded away into the fabric of spacetime itself. This is where the journey takes a fascinating turn, connecting string theory directly to the holographic principle. Within the vast landscape of string theory, a specific and powerful realization of holography emerged, known as the anti-de Sitter/conformal field theory correspondence, or AD-S/CFT for short. Proposed by physicist Juan Maldacena in 1997, this duality provides a concrete, mathematical example of the holographic principle in action. It establishes an astonishing equivalence between two seemingly completely different worlds. On one side of this correspondence, you have a universe governed by gravity, a particular type of universe known as anti-de Sitter space. This is a negatively curved, hyperboloid-shaped space that, for the purpose of this model, has 5 dimensions. Living in this 5-dimensional bulk space are strings and other gravitational objects, all interacting according to the laws of string theory. On the other side of the duality, living on the 4-dimensional boundary that encloses this anti-de Sitter space, is a very different kind of theory, a conformal field theory. This is a quantum field theory similar to those that describe particles like electrons and quarks in our own universe, but with a special property: it has no gravity whatsoever. It's a purely quantum theory of particles interacting on a flat, lower-dimensional surface. The breathtaking claim of AD-S/CFT is that these two theories are completely equivalent. They are not just similar, they are two different descriptions of the exact same physical reality. Every single event, every interaction, every property in the 5-dimensional gravitational world has a perfect, one-to-one translation into the language of the 4-dimensional quantum world on the boundary, and vice versa. Calculating a complex gravitational interaction, like two black holes merging in the 5-dimensional bulk, is mathematically identical to calculating a specific pattern of particle interactions on the 4-dimensional boundary. The gravity and the extra dimensions are not fundamental. They emerge from the collective behavior of the quantum particles. This is the ultimate dimensional trick. A complex, messy system involving warped spacetime and gravitational forces in a higher dimensional world can be perfectly and completely described by a cleaner, gravity-free quantum theory operating in a world with one fewer dimension. It provides a precise, calculable blueprint for how a holographic universe could operate, demonstrating that the laws of physics do not necessarily require the dimensions we perceive. The richness of our experienced reality could indeed be a magnificent and consistent projection from a simpler, more fundamental realm operating on a distant surface. While the holographic principle began as a bold, almost philosophical conjecture, it needed a concrete mathematical foundation to be taken seriously by the wider physics community. That foundation arrived in a spectacular form in 1997, thanks to the brilliant work of a young physicist named Juan Maldacena. His proposal, now famously known as the anti-de Sitter/conformal field theory correspondence, or AD-S/CFT for short, provided a precise and stunningly elegant realization of holography. It wasn't just a suggestive idea anymore, it was a full-blown, calculable mathematical duality, a dictionary that could translate between two seemingly incompatible descriptions of reality. To grasp the sheer power of this correspondence, let's break down its two sides. On one hand, you have the bulk of this model universe, a 5-dimensional space known as anti-de Sitter space. Imagine this not as a flat, expansive realm like our own, but as a kind of hyperbolic, saddle-shaped geometry that is negatively curved. In this 5-dimensional bulk, the laws of physics include gravity, described by a version of string theory. Here, strings vibrate, black holes can form and evaporate, and the full force of Einstein's general relativity holds sway. It's a complete gravitational universe, just with one extra spatial dimension. Now picture the boundary that encloses this 5-dimensional universe. This boundary is a 4-dimensional world, 3 spatial dimensions plus time, much like our own. But the physics living on this boundary is utterly different. It is a conformal field theory, a specific type of quantum field theory that describes the interactions of particles without any mention of gravity whatsoever. It's a world of quarks, electrons, and photons interacting through quantum forces on a perfectly flat stage where gravity simply doesn't exist. These two descriptions, a gravitational theory in 5 dimensions and a non-gravitational quantum theory in 4 dimensions, appear completely separate and independent. The revolutionary heart of Maldacena's discovery is the claim that these two theories are not just similar, they are exactly equivalent. They are two different languages describing the very same underlying reality. This is the ultimate dictionary. Every single event, object, or process occurring in the 5-dimensional gravitational bulk has a perfect, one-to-one translation into the language of particles and quantum interactions on the 4-dimensional boundary. Want to calculate what happens when 2 black holes collide in that 5-dimensional world? You could painstakingly work through the complex equations of gravity and warped spacetime. Or you could instead perform a calculation involving the behavior of a specific type of plasma of interacting particles on the flat boundary. The two answers will be identical. The mind-bending implication is that gravity, the force that shapes planets and galaxies, is not a fundamental force at all in this framework. It is an emergent phenomenon, a collective illusion that arises from the complex, entangled quantum interactions of particles living on a lower dimensional surface where gravity doesn't even exist. A helpful, though imperfect, analogy is to think of a movie. The rich, 3-dimensional world you see on the screen, the depth, the movement, the drama, is not actually happening inside the projector. All of that information is encoded on the 2-dimensional surface of the film reel. The projector simply translates that flat data into the immersive experience. In the AD/CFT correspondence, the 4-dimensional quantum field theory is the film reel containing all the information. The 5-dimensional universe with its gravity and black holes is the projected movie, the spectacular illusion that emerges from that data. This duality provides physicists with an incredibly powerful tool. Problems that are impossibly difficult to solve in the gravitational description often become much more manageable when translated into the language of the quantum field theory on the boundary. It's like solving a complex puzzle by turning it into a different, easier puzzle with the exact same solution. This has opened up new avenues for understanding the behavior of black holes, the nature of quark-gluon plasmas created in particle accelerators, and even the strange properties of certain exotic materials. The AD/CFT correspondence is more than a mathematical curiosity. It is a working prototype of a holographic universe, demonstrating with rigorous precision that the dimensions we experience and the forces we feel might be the grandest emergent story ever told. But if the holographic principle is a fundamental property of our universe and not just a mathematical curiosity, shouldn't there be some way to test it? This is the critical bridge between breathtaking theory and observable reality, and it's a challenge physicists are actively tackling. The central obstacle is scale. The hypothetical pixels of our cosmic hologram, if they exist, are thought to be unimaginably small, on the order of the Planck length, a scale a billion times smaller than an atom. Probing this directly is far beyond the reach of any particle collider we could ever build. So, scientists have had to become incredibly creative, looking for indirect signatures and clever analogies in systems we can actually study. One of the most promising avenues involves looking for holographic noise. The idea is that if spacetime itself is fundamentally pixelated, a projection from a 2-dimensional surface, then it shouldn't be perfectly smooth. At the tiniest possible scales, it should have a faint fuzziness or jitter, a quantum uncertainty in the position of everything. This isn't the jitter of particles, but a jitter of the stage itself. Several ambitious experiments are designed to detect this. The holometer or holographic interferometer at Fermilab is a prime example. It uses two powerful laser interferometers placed close together to see if the fabric of space itself vibrates. The lasers are shot down perpendicular arms and reflected back. If the distance the light travels fluctuates in a correlated way between the two devices, it could be a sign that both are being shaken by the same underlying holographic noise. While the holometer hasn't found definitive evidence yet, it has placed new limits on this potential spacetime jitter, ruling out some specific models and paving the way for even more sensitive future experiments. Another fascinating approach looks to the very beginning of the universe. The cosmic microwave background, the faint afterglow of the Big Bang that fills the entire sky, is a fossil imprint from when the universe was just 380,000 years old. It is remarkably uniform, but not perfectly so. Tiny fluctuations in temperature reveal the seeds of all future cosmic structure. Some cosmologists propose that if the early universe was holographic, these temperature variations might carry a specific statistical signature, a subtle deviation from the predictions of standard inflationary cosmology. Scouring the exquisite data from telescopes like Planck for these specific patterns is like searching for a fingerprint left by a lower dimensional past. It's a monumental task akin to finding a single specific grain of sand on a vast beach, but the potential payoff is a direct glimpse into the fundamental architecture of reality. Perhaps the most surprising experimental connections are found not in space, but in the lab, through the study of exotic states of matter. There is a remarkable and unexpected mathematical equivalence between the equations describing certain gravitational systems in anti-de Sitter space and those describing the behavior of some superconductors and other strange quantum fluids. This means that a complex gravitational phenomenon, like the way information falls into a black hole, can be modeled by studying how electrons flow and entangle in a thin, two-dimensional sheet of material. In these lab systems, the third dimension effectively emerges from the collective behavior of the particles. Researchers have already observed phenomena in these materials, like entanglement entropy, that scale with the system's boundary area and not its volume, a direct echo of Bekenstein's black hole entropy finding. While this doesn't prove our universe is holographic, it provides a tangible, testable playground where the principles of holography manifest in a controlled setting, offering incredible support for the mathematical soundness of the idea and giving us a small-scale model of how dimensional emergence might actually work. If the holographic principle truly describes our universe, its implications would reach far beyond black holes and string theory, striking at the very heart of cosmology, the study of the universe's origin, evolution, and ultimate fate. This radical idea doesn't just add a new chapter to our cosmic story, it suggests we might need to rewrite the entire book from a completely different perspective. Imagine the grand narrative of the Big Bang, the formation of galaxies, and the mysterious forces pushing the cosmos apart, all being fundamentally reinterpreted through the lens of a simpler, lower-dimensional reality. The potential is staggering, offering fresh solutions to some of the most persistent puzzles in modern science. One of the most profound applications involves the very beginning of everything. The standard Big Bang model describes a singularity, a point of infinite density and temperature from which the universe explosively expanded. But this model has its own set of problems, and the holographic principle offers a compelling alternative. Some cosmologists propose that in its earliest moments, the universe wasn't a hot, dense, three-dimensional ball at all. Instead, it could have been a cold, low-energy, two-dimensional state. In this view, the Big Bang wasn't the beginning of space and time, But the moment when this primordial two-dimensional information structure heated up and projected itself into the three spatial dimensions we now inhabit. The universe didn't simply expand, it emerged like a three-dimensional image materializing from a flat, encoded surface. This transition from a 2D to a 3D state could explain why our universe appears to have a finite age and a specific starting point, not because of a singularity, but because that's when the holographic projection began. This holographic framework also provides elegant potential solutions to two of cosmology's greatest puzzles, the horizon problem and the nature of dark energy. The horizon problem asks why the universe looks so uniform in every direction. The cosmic microwave background, the remnant heat from the early universe, has almost exactly the same temperature whether we look north, south, east, or west. But in the Standard Model, these regions were too far apart to have ever been in contact, to have exchanged heat and reached equilibrium. It's like walking into a party and finding hundreds of strangers all wearing the exact same outfit without having ever communicated. The classic solution is a period of incredibly rapid expansion called inflation, which stretched a tiny, uniform patch to become our entire observable universe. However, the holographic principle offers a different, perhaps more natural explanation. If the early universe was effectively two-dimensional, the amount of information needed to describe it and the distances that information had to travel were vastly smaller. In a 2D state, everything could have been easily connected and equilibrated, creating that uniformity naturally before the projection into 3 dimensions even began. The horizon problem might simply vanish when you realize the early cosmos was far smaller and simpler than we thought. Then there's the mystery of dark energy, the mysterious force causing the expansion of the universe to accelerate. Its nature is completely unknown, and its observed value is notoriously difficult to reconcile with quantum field theory. But in a holographic cosmos, dark energy might not be a strange force or substance at all. It could be a consequence of the universe's information content and the way it is encoded on the boundary. The acceleration of expansion might be linked to the maximum amount of information that can be stored on our cosmic horizon, the ultimate informational boundary of our observable universe. It would be a thermodynamic effect, much like the pressure in a gas arises from the motion of its molecules, rather than a fundamental force. This approach naturally leads to a predicted value for dark energy that is much closer to what we actually observe, potentially solving a problem that has vexed physicists for decades. Even the enigmatic nature of dark matter, the invisible glue that holds galaxies together, could be reinterpreted. While it's less direct, some theories suggest that what we perceive as dark matter could be an emergent gravitational effect stemming from the underlying quantum entanglement on the holographic boundary. The extra gravitational pull we attribute to unseen matter might actually be a subtle distortion in the projected spacetime geometry, a kind of shadow cast by complex information processing happening on the lower dimensional surface. This doesn't mean dark matter particles don't exist, but it opens the door to a fascinating alternative where the missing mass of the universe is another illusion, another clue that we are reading the projection rather than the source code. By reconsidering our cosmic history through this holographic lens, we aren't just adding new ideas, we are fundamentally reshaping our understanding of why the universe looks and behaves the way it does, from its first moment to its ultimate destiny. For over a century, physics has been living with a profound and frustrating split personality. On one hand, we have general relativity, Albert Einstein's magnificent theory of gravity, which describes the cosmos on the grandest scales, the graceful dance of planets, the warping of spacetime around stars, and the crushing depths of black holes. It is a theory of smooth, geometric curves, of a deterministic universe where cause and effect are clearly defined. On the other hand, we have quantum mechanics, the wildly successful rules governing the subatomic world. This is a realm of probability, uncertainty, and ghostly entanglement, where particles can be in two places at once, and reality seems to remain undecided until it is measured. Both theories are spectacularly accurate within their own domains, but they are fundamentally, violently incompatible. When their equations are forced to meet, like at the center of a black hole or the moment of the Big Bang, the result is a mathematical disaster, a shower of infinities and contradictions that signals a complete breakdown of our understanding. Unifying these two pillars into a single, coherent theory of quantum gravity is perhaps the most sought-after goal in all of modern science, and it is a puzzle that has stubbornly resisted solution for decades. The core of the conflict lies in how each theory views the fabric of reality. In general relativity, spacetime is a smooth, continuous stage, a malleable canvas that can bend and stretch. In quantum mechanics, the universe is inherently grainy and probabilistic at the smallest scales. Trying to quantize gravity, to describe it in terms of discrete packets of energy called gravitons, runs into immense mathematical difficulties. The calculations become impossibly complex, producing infinite answers that make no physical sense. This is where the holographic principle doesn't just offer another theory, it offers a breathtakingly elegant escape route. It suggests that the problem isn't that gravity is hard to quantize, but that we've been trying to quantize the wrong thing. Gravity, according to holography, isn't a fundamental force to be quantized at all. It is an emergent phenomenon, a collective illusion that arises from something entirely different happening in a lower dimensional world. This is the revolutionary shift in perspective. Instead of struggling to force quantum rules onto gravity within our three-dimensional space, the holographic principle says we should look for the source of gravity outside of that space, on a two-dimensional boundary. In this view, gravity isn't primary, information is. The force we experience as gravity is a side effect, a consequence of the way information is entangled and processed on that lower dimensional surface. It's analogous to the way the concept of temperature emerges from the chaotic motion of countless molecules. You can't point to a single molecule and ask for its temperature. Temperature only has meaning as a collective, statistical property of the whole system. Similarly, gravity might only have meaning as a collective property of a vast network of quantum information. The bending of spacetime could be a story told by the changing patterns of entanglement between quantum bits on the boundary. This approach dramatically simplifies the mathematical nightmare of quantum gravity. How? By transferring the problem to a realm where gravity doesn't even exist. The most powerful example of this is the AD/CFT correspondence we discussed earlier. It provides a complete, consistent, and calculable duality. A problem involving strong gravity in a warped five-dimensional space, a problem that would be hopelessly complex using standard methods, becomes mathematically equivalent to a problem involving a well-behaved quantum field theory, living on a flat four-dimensional surface without any gravity. The insurmountable calculations of quantum gravity in the bulk are translated into far more manageable calculations of particle interactions on the boundary. It's like being given the answer key to the universe's hardest exam, but in a different language. Once you have the translation dictionary, what was once impossible becomes tractable. This doesn't just offer a technical shortcut, it provides a profound conceptual clarity. It suggests that the search for a theory of quantum gravity might have been looking in the wrong place all along. We've been trying to understand the source code of the universe by staring at the magnificent projected image, the three-dimensional movie. The holographic principle tells us to look instead at the projector, the two-dimensional film reel. The laws of physics governing that reel are quantum mechanical, but they are laws without gravity. The gravity we experience is part of the story the movie tells. This framework has already yielded incredible insights, particularly into the nature of black holes and the preservation of information, resolving paradoxes that once seemed intractable. By bridging the gap with fewer dimensions, the holographic principle doesn't just add another contender to the race for quantum gravity. It changes the very track the race is run on, offering a path to the unified theory that has eluded us for so long by showing us that the unity was there all along, just hidden in a simpler, lower-dimensional description. This shift in perspective leads us to a truly staggering possibility. If the universe is a holographic projection, then what is the true nature of the thing being projected? The answer, according to a growing number of physicists and information theorists, is not matter or energy, but something far more fundamental: information itself. This is the core idea of the digital physics, or it from bit philosophy, championed by visionaries like John Archibald Wheeler. It suggests that at its most basic level, every particle, every force field, and even the fabric of spacetime is not the primary reality. Instead, they are manifestations of information, bits of data being processed according to a set of cosmic rules. In this view, the universe isn't just described by information, it literally is information. The chair you're sitting on, the air you're breathing, the stars in the sky, all of it could be the output of an unimaginably vast computation. If reality is fundamentally informational, then the laws of physics we've worked so hard to discover are not the bedrock laws of matter, but the operating system's algorithms. They are the software code that governs how information is updated, transformed, and interacts. Gravity, electromagnetism, and the nuclear forces wouldn't be fundamental forces but emergent properties of this underlying information processing. Much like the behavior of a video game character emerges from the game's code rather than from any physical laws inside the television. This provides an elegant explanation for why our universe is so mathematical. We aren't discovering independent mathematical truths. We are reverse engineering the source code of a reality that is, at its heart, a mathematical structure. The astonishing effectiveness of mathematics in the natural sciences, a puzzle that has perplexed philosophers for centuries, suddenly makes perfect sense if the universe is literally running on math. This idea finds a powerful partner in the concept of quantum computation. A standard classical computer uses bits that are either a 0 or a 1. A quantum computer, however, uses quantum bits or qubits, which can exist in a superposition of both 0 and 1 simultaneously. This allows it to perform many calculations in parallel, offering a staggering increase in processing power for certain problems. Now, consider the quantum world our universe is built upon. Particles are constantly in a fuzzy state of superposition. They become entangled across vast distances, and their properties remain undecided until measured. This sounds less like the deterministic clockwork of a classical machine and far more like the frenetic, parallel processing of a quantum computer. The holographic principle adds a breathtaking layer to this. The vast, distributed network of qubits processing the cosmic code might not be located in our three-dimensional space. They could be the fundamental degrees of freedom on the lower dimensional boundary, and our entire experienced reality is the result of this monumental quantum computation being run. This perspective forces us to confront some of the deepest questions about our own existence, namely the age-old debate between free will and determinism. If the universe is a computer, does that mean everything is predetermined by its initial code? Is our sense of choice and agency just an illusion, a convincing narrative generated by the algorithm? The answer might be more nuanced than a simple yes or no. In a purely classical, deterministic computer, the outcome is indeed fixed from the start, but our universe appears to be quantum, and quantum mechanics is inherently probabilistic. Its outcomes are not predetermined with certainty, they are governed by probabilities. This introduces a fundamental element of randomness at the core of reality. Your choices might not be pre-written in a cosmic script, but instead emerge from a complex interplay of algorithmic process and genuine quantum uncertainty. Your brain, itself a sophisticated information processing system, could be engaging with the universe's quantum computational layer, making decisions that are neither completely random nor completely predetermined, but truly emergent and authentic. This doesn't prove free will in a philosophical sense, but it does open a door for it within a scientific framework, suggesting that our experience of making choices could be a real feature of how the cosmic computer operates, not just a bug in our perception. So if our reality is a kind of cosmic projection, a magnificent illusion emerging from a simpler, lower-dimensional source, what does that actually say about the world we live in and our place within it? This is where the conversation shifts from the equations of physics to the profound questions of philosophy, touching on the very nature of what is real and what it means to exist. For centuries, philosophers have debated whether our senses reveal the true nature of reality or merely a useful representation of it. The holographic principle doesn't just add a new voice to this ancient debate, it amplifies it with the full force of modern scientific discovery, suggesting that the answer might be stranger than any pure philosopher could have ever imagined. Consider the simple act of looking at a tree. Your eyes capture light reflecting off its leaves, your brain processes that information, and you perceive a solid, three-dimensional object existing independently in space. We take this for granted as an objective fact, but the holographic model proposes that the tree's solidity, its color, its very existence as a separate entity are all part of a consistent and interactive story generated from underlying data. It is real to you in the same way a character in an incredibly immersive virtual reality simulation is real to the person experiencing it. The character has agency, the environment responds, the story unfolds, but it is all emerging from lines of code. This doesn't make the experience any less meaningful or the emotions any less genuine for the participant. Similarly, our reality is no less real to us because it might be emergent. The laws of physics still apply, cause and effect are consistent, and our experiences are undeniably vivid. The holographic principle doesn't claim that reality is an illusion in the sense of being fake or unimportant. Rather, it suggests that its fundamental nature is different from our perception of it. The tree is not fundamentally a collection of atoms in a void. It is a manifestation of information and relationship, a node in a cosmic network whose true workings occur on a boundary we cannot see. This forces a radical rethinking of objectivity. We like to believe in an objective world out there, a universe that exists independently of any observer. But if that world is a projection, the very idea of a detached, God's-eye view of reality might be impossible. Our perception of an objective world could itself be a feature of the projection, a necessary part of the story to make it consistent and navigable. This echoes ideas from neuroscience which show that our brains are not passive cameras recording the world. They are active prediction engines, constantly constructing our experience of reality based on sensory inputs and prior expectations. What we perceive is already a highly processed interpretation, a user interface designed for survival, not a direct readout of absolute truth. The holographic principle takes this a step further. suggesting that the stage upon which this neurological drama plays out space and time themselves is also part of that constructed interface. The objective world and the subjective observer might not be as separate as we think. They could be deeply intertwined aspects of the same informational process. And what then of consciousness? This is the deepest and most perplexing ramification. If the universe is information being processed, then what is the nature of the thing that is experiencing it? Is consciousness itself emergent from the complexity of this information processing, a flicker of self-awareness in the projected simulation? Or could it be something more fundamental, perhaps even the reason the projection exists in the first place? Some interpretations, leaning on ideals from quantum mechanics, suggest that observation might play a key role in translating potentiality into actuality. In a holographic framework, this could mean that consciousness isn't just a passive viewer of the movie, but an integral participant in its rendering. This doesn't mean we individually control reality with our thoughts, but that conscious observation could be a fundamental process through which the coherent, classical world emerges from the fuzzy, probabilistic quantum information on the boundary. It places us not as outsiders looking in, but as deeply embedded features of the cosmos, our awareness intrinsically linked to the manifestation of reality itself. This perspective bridges the gap between the cold, hard data of physics and the intimate, undeniable reality of our own experience, suggesting that the quest to understand the universe and the quest to understand ourselves are ultimately one and the same. Long before the holographic principle was a serious topic in physics departments, a similar vein of thought was already captivating the public imagination through the powerful lens of science fiction. The idea that our reality might not be what it seems that it could be, a projection, a simulation, or an elaborate construct, has been a fertile ground for storytellers for decades, offering a potent metaphor for exploring questions of identity, control, and the nature of existence itself. Perhaps the most iconic example is the 1999 film The Matrix, which presented a world where humanity is unknowingly trapped in a simulated reality, their bodies powering a vast machine while their minds experience a perfectly convincing digital world. While the movie's premise is more about artificial intelligence and computer simulation than the specific physics of the holographic principle, the central theme resonates deeply. It captures that same unsettling and exhilarating feeling that the solid world around us might be a kind of interface, a grand illusion masking a simpler and perhaps more terrifying underlying truth. The film's cultural impact was seismic, introducing phrases like "red pill" into the lexicon as a shorthand for choosing to see the harsh truth over comfortable illusion, a concept that many who explore these scientific ideas can intimately relate to. This fascination isn't confined to the silver screen. In the realm of literature, Michael Talbot's 1991 book, The Holographic Universe, played a pivotal role in bringing these ideas to a mass audience, though it blended scientific concepts with more mystical and paranormal interpretations. Talbot drew heavily on the work of neurophysiologist Carl Pribram and physicist David Bohm, who themselves had proposed a holographic model of the brain and the universe. The book argued that a holographic cosmos could explain a wide range of phenomena, from psychic abilities and synchronicities to the nature of healing and religious experiences. While Talbot's work was inspirational for many, it also exemplifies how scientific ideas can be stretched and reinterpreted in popular culture, sometimes drifting far from their original, rigorous mathematical foundations. The book created a bridge between theoretical physics and New Age spirituality, making the concept accessible but also seeding a number of misconceptions that physicists still grapple with today when speaking to public audiences. These cultural touchstones are incredibly valuable because they act as a gateway, sparking curiosity and making abstract, complex ideas feel immediate and personal. They allow people to engage with the profound philosophical questions raised by holography without needing to understand the intricate math of the AD/CFT correspondence. A person who has never heard of Juan Maldacena might still have spent hours discussing the nature of reality after watching The Matrix. This pop culture presence democratizes the wonder of these concepts, inviting everyone into the conversation. However, this widespread exposure comes with a significant caveat. The artistic and narrative needs of a film or a book often prioritize drama and metaphor over scientific accuracy. The danger is that the public's understanding can become anchored to these fictionalized versions, leading to persistent confusions. For instance, the holographic principle is frequently conflated with the simulation hypothesis, the idea that our universe is a computer program run by an advanced civilization. While both ideas play with the concept of reality as an illusion, they are fundamentally different. The simulation hypothesis is a technological speculation, a possibility about who might be running the code. The holographic principle, in contrast, is a proposed law of nature, a statement about how the universe fundamentally operates at its most basic level, with or without any outside programmer. It's about the architecture of reality itself, not its potential authorship. This blurring of lines is perhaps the most significant impact of pop culture on the public perception of this science. It can lead to a kind of scientific telephone game where the nuanced, peer-reviewed theory becomes simplified and mixed with other concepts until it's nearly unrecognizable. You might hear people say they believe in a holographic universe because they've had a déjà vu or a strange coincidence, attributing personal experiences to a grand cosmological model in a way most physicists would find unrelated. This isn't to dismiss the value of wonder or personal connection, but it highlights the challenge scientists face in communication. They must honor the public's fascination, often ignited by pop culture, while carefully clarifying what the theory actually says and what it doesn't. The cultural journey of the holographic principle, from obscure physics papers to blockbuster movies and best-selling books, is a testament to its raw power to captivate the human spirit. It shows that at its heart, this isn't just a dry mathematical exercise. It's an idea that touches on the very core of who we are and what we believe to be real, making it one of the most human scientific discoveries of our time. Of course, such a radical rethinking of reality was never going to be universally accepted without a healthy dose of skepticism. For all its elegance and problem-solving power, the holographic principle faces significant and serious criticisms from within the physics community. It's crucial to remember that this is how good science works, through rigorous debate, challenging assumptions, and demanding evidence. The most common and perhaps most damning criticism is the stark lack of direct, testable evidence. While we discussed the creative searches for holographic noise or signatures in the cosmic microwave background, the truth is that these are incredibly speculative long shots. No experiment has yet confirmed any prediction unique to the holographic principle that cannot be explained by more conventional theories. For many empirically minded physicists, an idea that remains almost entirely in the realm of beautiful mathematics without concrete data to back it up is more philosophy than science. It risks becoming an elegant story that's intellectually satisfying but ultimately untethered from observable reality. Another major hurdle is a very specific and technical mismatch between the principle's most successful formulation and the universe we actually live in. The stunningly precise AD/CFT correspondence, our best mathematical blueprint for holography, relies on a universe with a specific type of geometry called anti-de Sitter space. This is a universe with negative curvature, a kind of saddle-shaped geometry that crucially has a boundary in both space and time that information can be encoded on. But our real universe, according to overwhelming astronomical evidence, is not like that. Measurements of the cosmic microwave background and the acceleration of expansion tell us we live in a universe that is very nearly flat and is dominated by a positive energy density, a cosmos that much more closely resembles what's called de Sitter space. Unlike anti-de Sitter space does not have a convenient, accessible boundary in space and time to store all this information. It's a closed structure. So, critics argue, we've built this magnificent mathematical castle for holography, but it's on the wrong planet. Translating the principles of AD/CFT to our de Sitter-like universe, a challenge sometimes called DS/CFT, has proven to be incredibly difficult and nowhere near as successful or well-defined. This doesn't necessarily kill the idea, but it severely limits its direct applicability to the one universe we're trying to explain. Furthermore, some physicists worry that the holographic principle, in its effort to solve certain problems, might simply be creating new ones. If our three-dimensional world is an illusion, then the illusion is astonishingly persistent and perfectly consistent. The principle must then explain not just how the projection works, but why it is so flawlessly convincing. Why do we have such a powerful and unshakable intuition of a three-dimensional reality if it's not fundamental? How does the precise, local physics we observe at every scale, from the trajectory of a baseball to the orbit of a planet, emerge so perfectly from a non-local, lower-dimensional description? These are not trivial questions. In some ways, accepting the holographic principle requires a leap of faith that the complex emergence always works perfectly, which to some critics feels like replacing one mystery with another. There's also a concern that the focus on such a grand, all-encompassing idea might distract from more modest, incremental approaches to quantum gravity that could be more fruitful in the short term, like loop quantum gravity or causal set theory. Yet, in the face of these strong criticisms, proponents of the holographic principle have developed thoughtful counterarguments. They readily admit the lack of direct evidence but argue that this is true for almost all approaches to quantum gravity. We are simply in an era where the energy scales required for direct testing are beyond our reach. They point to the indirect evidence as being profoundly suggestive. The way the principle naturally resolves the black hole information paradox is for them a huge point in its favor, solving a decades-old problem that other theories struggle with. It's a theoretical triumph that shouldn't be dismissed just because we can't yet touch it in a lab. Regarding the de Sitter space problem, researchers are actively working on formulations of holography for our type of universe. While DS/CFT is not as mature as its AD/S cousin, progress is being made, suggesting the core idea might be more flexible than it first appears. The challenge of our universe might not be a fatal flaw, but the next great puzzle to be solved within the holographic framework. And on the point of creating new problems, advocates would argue that this is the very nature of scientific revolution. Every major paradigm shift in physics, from Copernicus moving the sun to the center to Einstein warping spacetime, initially created more questions than it answered. The fact that the holographic principle forces us to ask entirely new kinds of questions about emergence, locality, and the nature of information is seen not as a weakness but as its greatest strength. It is pushing the boundaries of what we think is possible and forcing a deeper conversation about the foundations of reality. This vibrant and ongoing debate is a sign of a healthy, living science. It shows that the holographic principle is not a settled dogma but a dynamic, evolving idea being stress-tested from every angle. This rigorous process of criticism and response is what will ultimately determine whether it becomes a cornerstone of our understanding of the cosmos or a fascinating but ultimately incorrect detour in the long quest for a theory of everything. While the holographic principle presents a captivating vision of reality as a projection, it is far from the only ambitious framework vying to become the ultimate theory of everything. The quest to unify general relativity and quantum mechanics is a sprawling intellectual frontier, and several other powerful ideas offer radically different solutions to the same fundamental puzzle. Each of these alternatives starts from a unique set of assumptions and builds a distinct picture of spacetime's nature, providing a crucial broader context that highlights just how revolutionary and how specific the holographic approach truly is. One of the most prominent rivals is loop quantum gravity. Unlike string theory and its holographic offspring, which propose that reality is built from tiny vibrating strings, loop quantum gravity takes a more direct approach. It doesn't add extra dimensions or suggest that gravity is emergent. Instead, it applies the rules of quantum mechanics directly to the fabric of spacetime itself, as described by Einstein's general relativity. The theory's central and beautiful insight is that space is not infinitely divisible. It proposes that spacetime is woven from a network of tiny, discrete, one-dimensional loops, hence the name. These loops form a kind of evolving spin network, a tapestry of finite threads where each knot represents a tiny, quantized volume of space. This means that at the Planck scale, space is granular, not smooth, a fabric made of individual threads rather than a continuous sheet. This granularity naturally prevents the infinities that plague other theories when describing the center of a black hole or the moment of the Big Bang. In fact, loop quantum gravity suggests the Big Bang might not have been a singularity at all, but rather a big bounce, a moment where a previous universe collapsed and then re-expanded into our own. This stands in stark contrast to the holographic principle. Loop quantum gravity keeps gravity as a fundamental force and our universe firmly in three spatial dimensions, seeking to quantize the stage itself, whereas holography suggests the stage is an illusion emerging from a simpler play written on a lower dimensional surface. Another fascinating, though less well-known, competitor is causal dynamical triangulation. This theory takes a radically practical, computational approach to the problem of quantum gravity. It makes a very simple starting assumption. Spacetime is fundamentally made of tiny, basic building blocks. The theorists behind this approach use two-dimensional triangles or four-dimensional simplices, the multi-dimensional equivalent of a triangle, as their elementary pieces. They then write a computer program that randomly assembles vast numbers of these tiny shapes, connecting them together to build a model universe. But there's a crucial rule: the assembly must respect causality, meaning cause must always precede effect in the connections between pieces. The astonishing result is that when the program runs and you zoom out from the frenetic, chaotic jumble of microscopic triangles, a smooth, four-dimensional spacetime emerges all on its own. It's like watching a pointillist painting resolve into a clear image as you step back. This approach doesn't require strings, extra dimensions, or a holographic boundary. It shows how the familiar geometry of our universe could spontaneously arise from the random, causal connection of simple parts. It is a powerful demonstration that the smooth continuity of spacetime could be a large-scale illusion, but one that emerges from a different kind of underlying discreteness than the holographic principle proposes. Then there are theories that, like holography, argue that gravity is not a fundamental force. The most notable is Eric Verland's theory of emergent gravity. Verland proposed a shocking idea. Gravity doesn't exist as a fundamental force in the same way that electromagnetism does. Instead, it is an entropic force. This means it emerges from the natural tendency of systems to move towards disorder, much like how the pressure in a gas emerges from the random motion of molecules. Verlaine's inspiration came directly from the holographic principle's link between gravity and thermodynamics. He suggests that what we perceive as gravity is actually a consequence of changes in the information content, or entropy, associated with the positions of material bodies. When you move an object, you are effectively changing the amount of information in the underlying microscopic structure of spacetime, and the force we call gravity is a resistance to that change. This is a profound and mind-bending concept that completely reframes gravity, linking it to information theory in a way that is distinct from, yet spiritually aligned with, the holographic principle. It suggests a deep and fundamental connection between the laws of gravity and the laws of information and thermodynamics, but it does so without necessarily invoking a full holographic duality with a lower dimensional boundary. Comparing these theories reveals a fascinating spectrum of thought. The holographic principle and emergent gravity both argue for a universe where our experienced reality is not fundamental, though they differ on the precise mechanism. Loop quantum gravity and causal dynamical triangulation, on the other hand, take spacetime more at face value but argue it has a discrete, atomic structure at the smallest scales. This diversity is not a weakness of theoretical physics, it is its greatest strength. Each approach attacks the problem from a different angle, revealing new insights and challenging the assumptions of the others. The holographic principle's power lies in its ability to solve the black hole information paradox and provide a mathematical toolkit through AD/CFT. Loop quantum gravity's strength is its direct quantization of spacetime without extra dimensions. Causal dynamical triangulation offers a compelling proof of concept that our universe's geometry can emerge from simple rules. And emergent gravity challenges our very definition of a fundamental force. Together, they form a rich ecosystem of ideas, each a different path through the same dark forest, all striving toward the same glorious goal, a single, coherent theory that explains the universe in its entirety. But what are the actual tools that allow physicists to even conceive of such a profound trick? The holographic principle isn't built on whimsical speculation. It's constructed from a formidable framework of advanced mathematics that gives the idea its rigor and predictive power. To truly appreciate how a lower dimensional description can encode a higher dimensional reality, we need to peek under the hood at a few of the key concepts that make it all work, translating their complex language into something more intuitive. It starts with a deep connection between information, disorder, and geometry, a connection first revealed by a black hole's most unexpected property. The journey into this mathematical landscape begins with entropy. In our everyday experience, we understand entropy as a measure of disorder. Think of a clean room gradually becoming messy over time. In physics and information theory, entropy is more precisely a measure of uncertainty or hidden information. It quantifies the number of different ways a system can be arranged on the inside while looking the same on the outside. Jacob Bekenstein's revolutionary insight was that a black hole's entropy is not proportional to its volume, but to the area of its event horizon. This was the first concrete hint that the information content of a three-dimensional region might be bound by its two-dimensional surface. The mathematics behind this is profound. The formula for black hole entropy is stunningly simple. S equals a/4, where S is the entropy and A is the area of the horizon, with the constants ensuring the units are correct. This elegant equation suggests a fundamental limit. The maximum amount of information that can be stored in any region of space is directly proportional to its surface area, not its volume. It's as if the universe has a built-in resolution limit, and that limit is defined by boundaries. This area law entropy is the cornerstone upon which the entire holographic edifice is built, providing a precise mathematical link between geometry and information. Another indispensable tool in this toolkit is conformal symmetry. This is a very special and powerful kind of symmetry. While we're familiar with symmetries like rotation or reflection, which preserve shapes and distances, conformal symmetry is more subtle. It preserves angles but allows distances to scale up or down. Imagine a detailed image on a rubber sheet. If you stretch or shrink the sheet uniformly, the relative angles between lines in the image stay the same, even though the overall size changes. Theories with this property, called conformal field theories, are incredibly important because they often don't have a built-in scale. They look the same at different magnifications. This makes them mathematically tractable and robust. In the AD/CFT correspondence, the quantum field theory living on the lower dimensional boundary is conformal. This symmetry is the magic that allows the translation between dimensions to work. The conformal symmetry on the boundary perfectly mirrors the gravitational symmetry in the higher dimensional bulk, acting as a kind of mathematical Rosetta Stone that ensures a perfect dictionary between the two descriptions of the same reality. To visualize how information on a boundary could possibly build a universe, physicists use the concept of tensor networks. Imagine you want to create a highly complex image, like a detailed landscape painting. Instead of painting it directly, you could break it down into a massive network of tiny, simple stamps, each contributing a small piece of the overall picture. A tensor network is the mathematical version of this. It's a web of interconnected nodes where each node is a small multidimensional array of numbers, a tensor. That represents a small piece of information or a simple quantum state. The connections between these nodes represent quantum entanglement. By entangling these simple building blocks in a specific pattern across a flat, two-dimensional network, a remarkable thing happens. The collective state of the entire network describes the physics of a higher dimensional space. The three-dimensional volume emerges from the intricate web of connections on the two-dimensional surface. These networks provide a powerful and intuitive model for holography, showing how complexity and dimension can literally arise from the way information is woven together through quantum links. Finally, we have the geometry of anti-de Sitter space itself, the HYPERBOLIC Chinese letter where the most precise form of holography plays out. Our intuitive notion of geometry is flat, like a sheet of paper, or spherical, like a ball. Anti-de Sitter space is hyperbolic, meaning it's curved like a saddle or an endless series of interconnected lobes. This negative curvature has a strange property. Its volume grows exponentially as you move outward from the center, much faster than in flat space. But this vast interior is completely described by physics happening on its boundary, which has one less dimension. The mathematical maps between these two spaces rely on solving complex equations involving this curvature. The gravity in the warped bulk is described by Einstein's equations from general relativity, while the particles on the flat boundary are described by the probability waves of quantum field theory. The mathematics proves these two sets of equations, once seen as irreconcilable enemies, are two sides of the same coin. This is the true magic of the mathematical foundation. It doesn't just suggest a duality. It provides the rigorous, calculable proof that the laws of physics can be completely translated from one dimension to another, revealing a hidden unity at the heart of reality that is both elegant and awe-inspiring. While the holographic principle remains a profound theoretical framework for understanding the cosmos, its most surprising impact might not be in telescopes or particle accelerators, but in the technology that could reshape our daily lives. The idea that a lower dimensional description can encode the complex information of a higher dimensional reality isn't just a mind-bending concept for physicists, it's a powerful engine for innovation, already beginning to influence fields from computing to cryptography. This translation from abstract theory to tangible technology demonstrates how questioning the fundamental nature of reality can yield tools that transform our world, proving that the most esoteric science often holds the key to the most practical breakthroughs. One of the most immediate and exciting applications lies in the burgeoning field of quantum computing. Today's quantum computers are incredibly fragile. Their qubits, the basic units of quantum information, are prone to decoherence, easily disturbed by minor fluctuations in their environment. This is where insights from the AD/CFT correspondence become unexpectedly valuable. This duality is, at its heart, a powerful dictionary for translating problems between a quantum system and a gravitational one. Researchers have realized that the way information is scrambled and protected across a network of entangled particles in a quantum computer bears a striking mathematical resemblance to how information is encoded on the event horizon of a black hole in the holographic model. By using the mathematical tools developed for holography, scientists can design new algorithms and quantum error-correcting codes that are far more robust. These holographic codes work by distributing information across many qubits in a highly entangled state, much like how a hologram spreads image data across its entire surface. If one qubit fails or is lost, the information isn't gone. It can be reconstructed from the entangled state of the others, making the entire system significantly more fault-tolerant. This approach, inspired by how black holes preserve information, could be the crucial innovation that finally allows us to build large-scale, stable quantum computers capable of solving problems that are currently impossible. The connection to information storage goes even deeper. The core tenet of the holographic principle that the information content of a region is bound by its surface area, not its volume, suggests a fundamental physical limit to data density. This isn't just a theoretical curiosity. It implies that there is a maximum amount of information that can possibly be stored in any given space, a concept that could guide the future of data storage technology. While we are nowhere near hitting this ultimate Bekenstein bound, the principle inspires engineers to think in new ways about efficient information packing. More concretely, conventional holographic data storage is already a commercial reality, though it uses classical optics rather than quantum gravity. You can find it in the security holograms on your credit card and passport, which store a three-dimensional image on a two-dimensional film. Future advancements, perhaps informed by the quantum entanglement aspects of the holographic principle, could lead to storage devices with unprecedented density and durability, where data is not written in a specific location, but is instead distributed and protected across the entire medium through intricate quantum patterns. Beyond computing, the principles of holography are influencing the design of entirely new materials. This is perhaps one of the most surprising and powerful cross-pollinations of ideas. Scientists studying strange states of matter, like high-temperature superconductors, have found that their behavior is incredibly difficult to model with standard equations. Intriguingly, the mathematical description of electrons flowing with zero resistance in a thin, two-dimensional sheet of superconducting material can be precisely mapped onto the equations describing a black hole in a higher dimensional anti-de Sitter space. This means a physicist can take a complex problem in condensed matter physics, like understanding how a new superconductor works, translate it into a problem about gravity and black holes using the add-s/CFT dictionary, solve the gravitational problem, which is often mathematically simpler, and then translate the answer back to understand the superconductor. This holographic duality has become an unexpected but powerful tool for predicting the properties of novel materials, guiding researchers toward compounds that could lead to lossless power grids, ultra-fast quantum sensors, and other technologies that sound like science fiction. The abstract physics of black holes is quite literally helping us design the next generation of earthly technology. Ultimately, the greatest technological application of the holographic principle may be a shift in perspective itself. It teaches us that emergence, where complex behavior arises from simple rules, is a powerful design principle. Engineers and computer scientists are now looking to nature not just for specific blueprints, but for these overarching strategies. The lesson from holography is that you can create immense complexity and resilience not by building intricate, fragile structures, but by finding the right way to encode information through relationships and connections. This philosophy is already influencing the design of neural networks, the development of new encryption methods, and the planning of future communication networks. The holographic principle shows that the universe itself might be the most sophisticated computer, and by learning its deepest computational secrets, how it builds a three-dimensional world from a two-dimensional code, we are unlocking a new era of innovation that mirrors the fundamental architecture of reality itself. So how do you even begin to explain a concept this abstract? An idea that so thoroughly upends our intuitive grasp of reality? The challenge of communicating the holographic principle is a fascinating puzzle in itself, one that demands more than just reciting equations. It requires building a bridge of understanding, using creative tools and thoughtful analogies to guide someone from the solid world they know into this startling new perspective, all without losing the profound truth of the theory in the process. The goal isn't to water down the science, but to find the right language, a vocabulary of imagination that makes the incredible plausible. This is the heart of great science communication. It's not about simplification, but about translation. It's about finding the clearest path to that wonderful moment of insight, where a complex idea suddenly clicks into place, not because it was made trivial, but because it was made clear. One of the most powerful tools in this endeavor is the strategic use of analogy. We've already touched on a few, like comparing the universe to a hologram or a movie projection. But to make these stick, they need to be fleshed out and connected to everyday experience. A particularly effective analogy is that of a video game. Imagine a vast, open-world game with incredibly detailed graphics, dynamic weather systems, and non-player characters that seem to live their own lives. To the player immersed in this world, it feels expansive, three-dimensional, and real. But every single element of that reality, the mountain ranges, the changing light, the complex behaviors, is being rendered in real time from information stored on the game's disk or a remote server, which is essentially a two-dimensional surface. The player never sees the code, they experience the result. This mirrors the holographic principle beautifully. Our experienced universe is the rendered game, breathtakingly complex and interactive. The fundamental laws, the source code, could be written on a distant, lower-dimensional boundary. This analogy helps sidestep the common misconception that a holographic universe is an illusion in the sense of being fake. The game is real to the player, the experience is genuine. The revelation is about where the reality is being processed and stored. Moving beyond analogies, interactive models and visualizations are invaluable. For younger students or public audiences, physical demonstrations can work wonders. A simple laser pointer and a holographic sticker from a credit card can physically show how a flat, patterned surface can produce a three-dimensional image that changes as you move around it. This isn't just a parlor trick. It's a direct, tangible demonstration of the core concept that a lower dimensional surface can encode a higher dimensional reality. For more advanced learners, interactive software and simulations are key. Imagine a program that allows you to manipulate a two-dimensional network of points connected by lines, representing a quantum state. As you adjust the entanglement between the points, the software calculates and displays the emergent three-dimensional geometry that this network describes. This allows students to literally play with the principles of holography, seeing with their own eyes how changing relationships on a flat screen can construct depth, curvature, and volume, providing an intuitive grasp of how spacetime itself might be built from quantum information. The role of the science communicator, then, is to be a careful and honest guide. It's crucial to be transparent about what we know, what we suspect, and what remains pure speculation. When using an analogy like the video game, it's important to immediately follow it by clarifying the differences. Unlike a game, there is no known external programmer. The code is likely a fundamental property of nature. This prevents the conversation from veering into unscientific territory like simulation theory, while still leveraging the analogy's explanatory power. The best communicators also empower their audience with the right questions rather than just providing answers. Instead of just stating that gravity might be emergent, they might pose it as a puzzle. If the information for a three-dimensional world is on a two-dimensional surface, what does that tell us about the force that seems to bind that world together? Could it be part of the story rather than the author? This invites active engagement and critical thinking, turning a lecture into a shared exploration. Ultimately, this effort at education and outreach is about more than just sharing a cool idea. It's an investment in the future of curiosity. By demystifying these frontiers of physics without diminishing their wonder, we can ignite a spark in a young student who might one day develop the mathematical framework for a holographic description of our own de Sitter universe. We can empower a citizenry to better distinguish between profound science and pseudoscience, and we can invite everyone to participate in the most breathtaking conversation there is, the collective human effort to understand the true nature of the cosmos and our place within it. The holographic principle isn't just a theory for physicists. It's a testament to the power of human imagination to reach beyond the apparent limits of reality, and sharing that power is one of the most important things we can do. So where does this incredible journey go next? The holographic principle has given us a breathtaking new lens through which to view the cosmos, but it's far from a finished story. In many ways, the real work is just beginning, with physicists around the world embarking on a new generation of research to test, refine, and expand this radical vision of reality. The path forward is lit by both profound theoretical puzzles and the tantalizing possibility of real-world experiments, each question pushing us closer to a potential revolution in our understanding of the universe. One of the most urgent and difficult challenges is adapting the principle to the universe we actually live in. As we've discussed, our most precise mathematical blueprint for holography, the AD/CFT Correspondence, describes a hypothetical universe with negative curvature and anti-de Sitter space. But our real cosmos, with its accelerated expansion driven by dark energy, is best described as a de Sitter space. This isn't just a minor technicality, it's a fundamental mismatch. De Sitter space behaves very differently. It has a horizon that surrounds us, and it lacks the convenient, accessible boundary that makes AD/CFT so powerful. This has sent theorists on a quest for a de Sitter version of the correspondence, often called DS/CFT. The goal is to find an equivalent duality that works for our own universe, but progress has been slow and thorny. Cracking this puzzle is perhaps the single most important theoretical hurdle. Success would not only validate the holographic principle as a description of our reality, but could also provide a completely new mathematical framework for understanding dark energy and the ultimate fate of our expanding cosmos. Researchers are exploring exotic ideas like theories with non-unitary evolution or complex geometries, trying to find the right key to unlock this door. Beyond the de Sitter problem, physicists are delving into even more abstract mathematical territories. One exciting frontier involves higher spin theories. In the Standard Model, particles have intrinsic angular momentum called spin. Photons are spin 1, electrons are spin 1/2, and the hypothetical graviton would be spin 2. Higher spin theories propose the existence of particles with much larger spin values, 3, 4, and beyond. These theories are incredibly symmetric and, in some limits, can become almost trivial to solve. Intriguingly, there is evidence that the holographic dual of a higher spin theory in the bulk could be a very simple quantum field theory on the boundary. This offers a potential sandbox for testing the limits of holography, a simpler playground where we can work out the precise dictionary between the bulk and boundary worlds in exquisite detail before applying those lessons to the more complex case of our own universe with its familiar particles and forces. Perhaps the most dynamic and rapidly advancing area of research is the deep and growing connection to quantum information theory. The discovery that quantum entanglement is the fundamental glue stitching together the fabric of spacetime has opened a floodgate of new ideas. Scientists are now using tools from quantum computation, like quantum complexity and tensor networks, to probe the very nature of the holographic mapping. They're asking questions like, how exactly is a volume of space encoded in the quantum information on its boundary? What kind of quantum circuit would you need to run to literally generate a spacetime geometry from scratch? This cross-pollination of fields is yielding stunning insights. For instance, the growth of a wormhole inside a black hole might be directly equivalent to the increasing computational complexity of the quantum state on the boundary. This isn't just abstract theorizing. It's providing new, tangible ways to think about the emergence of space and time, treating the universe not as a collection of things but as a vast, dynamic web of quantum information relationships. And of course, the Holy Grail remains experimental validation. While detecting Planck-scale holographic noise is a monumental challenge, the search is becoming increasingly sophisticated. Next-generation experiments are moving beyond the pioneering work of the holometer. Plans are underway for space-based interferometers that could use the entire Earth as a seismic isolation platform, or experiments that exploit the cold, controlled environment of atom interferometry to achieve unprecedented sensitivity. Cosmologists continue to mine the cosmic microwave background data from observatories like Planck and the upcoming James Webb Space Telescope, searching for any statistical anomaly, any faint whisper in the echo of the Big Bang that could be the signature of a holographic beginning. Furthermore, the unexpected laboratory applications continue to bear fruit. As we get better at engineering complex quantum materials and simulating them with powerful computers, we are effectively creating small-scale analogs of holographic systems right here on Earth, offering a practical, testable window into the physics that might govern the entire universe. The future of holography is a multi-front effort, a convergence of pure mathematics, quantum computing, cosmology, and materials science, all pointing toward a single, unifying truth about the nature of our reality. This remarkable idea that our reality might be a projection from a lower dimensional surface doesn't just live in the isolated world of theoretical physics. Its implications ripple outward, touching and potentially transforming a stunning array of other disciplines, from the hard logic of computer science to the messy, beautiful complexity of biology, and even the expressive realm of art. The holographic principle at its core is a theory about information, relationships, and how complexity emerges from simplicity. And that is a language spoken by many different fields, creating a vibrant crossroads for collaborative innovation and entirely new ways of seeing familiar problems. In the world of computer science, this influence is already yielding tangible results, particularly in the quest to build a stable quantum computer. As we discussed, these machines are incredibly fragile, their qubits easily disturbed by the slightest interaction with the outside environment. The solution to this decoherence problem might come from a direct application of holographic thinking, the way the AD/CFT correspondence protects information on a black hole's horizon, spreading it out and encoding it through quantum entanglement so that it can't be destroyed, is providing a radical blueprint for quantum error correction. Researchers are now designing what they call holographic codes. Instead of storing a bit of information in a single, vulnerable qubit, these codes distribute the information across a vast network of entangled qubits, much like a hologram stores a three-dimensional image across its entire two-dimensional surface. If one part of the network fails, the information isn't lost. It can be reconstructed from the state of the remaining qubits. This approach, inspired by the universe's own most extreme information preservation system, is helping us build computers that are not just faster, but fundamentally more resilient, turning a cosmic principle into a practical engineering guideline. The connections to biology are perhaps even more profound, though more speculative. Consider the human brain, an organ of astonishing complexity with nearly 100 billion neurons, each connected to thousands of others. How does this network give rise to a unified conscious experience, a sense of self? Some neuroscientists, like Carl Pribram, have long suggested that the brain itself might process information in a holographic way. His model proposed that memories aren't stored in one specific location, but are instead distributed across the entire cerebral cortex. An injury to a small part of the brain might degrade the clarity of a memory, but rarely erases it completely, much like how damaging a small piece of a holographic plate merely makes the overall image fuzzier without destroying it. While Pribram's specific model is not the same as the modern holographic principle in physics, the parallel is striking. It suggests that the same informational principles that might govern the cosmos, distribution, redundancy, and emergence from a network could also be at work within our own minds, offering a new framework for understanding the deepest mystery of all, consciousness itself. This idea of distributed information and resilience extends beyond the brain to genetics and cellular biology. The DNA in every one of your cells is constantly under assault from radiation and toxic chemicals, yet the genetic information it carries remains remarkably stable over a lifetime. This isn't just because of repair mechanisms, it's also due to the inherent redundancy of the genetic code. Information is distributed and protected. Furthermore, the development of an organism from a single fertilized egg into a complex being with trillions of cells is a breathtaking feat of emergent complexity. The simple, one-dimensional code of DNA guides the construction of a three-dimensional body in a process that is still not fully understood. Some biologists are beginning to explore whether the mathematical tools of holography and emergence could provide new models for this magnificent transformation, viewing the genetic code not just as a linear blueprint, but as a lower dimensional set of instructions from which a higher dimensional form emerges. Even the world of art finds a powerful resonance with these ideas. For decades, artists have used actual holography to create works that play with perception, light, and dimensionality. But more conceptually, the holographic principle provides a rich metaphor that inspires digital artists, sculptors, and filmmakers. How do you visually represent a universe where space and time are not fundamental? Artists are creating stunning visualizations of higher dimensional spaces, complex networks of light that represent quantum entanglement, and interactive installations that make the viewer question the nature of their own perception. These works do more than just illustrate a scientific theory. They translate its emotional and philosophical weight into a sensory experience. They communicate the wonder, the unease, and the awe that comes with realizing the solid ground beneath our feet might be a grand and beautiful illusion, fostering a public dialogue about science that is felt as much as it is understood. This cross-pollination of ideas is the true power of a paradigm shift in fundamental physics. It doesn't just change the equations in a textbook, it changes the way we think across the entire spectrum of human knowledge. The holographic principle offers a new lens, a lens focused on relationships over objects, on information over substance, and on emergence over reductionism. By applying this lens to computer science, we build better machines. By applying it to biology, we may uncover new secrets of life. And by applying it to art, we expand our collective imagination. It demonstrates that the deepest truths about the universe are not isolated to one field, but are universal keys that can unlock doors we didn't even know were closed, fostering a collaborative innovation that is far greater than the sum of its parts. Long before physicists ever wrote an equation about event horizons or quantum entanglement, the deepest human minds were already grappling with a haunting suspicion that the world presented to our senses might not be the whole story. This intuition that reality is not what it appears, that a deeper truth lies hidden beneath the surface of our perceptions, is one of the most enduring themes in the history of human thought. The holographic principle, for all its mathematical sophistication, is the latest chapter in this ancient conversation, a scientific echo of philosophical questions that have persisted for millennia. We can trace this thread all the way back to ancient Greece and Plato's powerful allegory of the cave, written around 380 BC. In this timeless thought experiment, Plato asks us to imagine a group of people who have lived their entire lives chained deep inside a cave, facing a blank wall. Behind them, a fire burns, and between the fire and the prisoners, people carry various objects, casting shadows onto the wall in front of the captives. For these prisoners, these flickering shadows are reality. They name them, discuss them, and believe them to be the entirety of existence. They have no conception of the three-dimensional objects, the people, or the fire behind them that are the true sources of the shadows. Plato's point was profound. He suggested that we are all like those prisoners. The world we experience through our senses, the solid objects, the colors, the sounds, are merely shadows on the wall of our cave. True reality, what he called the world of forms, is a higher, more perfect realm of ideal concepts that we can only access through reason and philosophy. The parallels to the holographic principle are striking. In both views, our everyday experience is a dim projection, a limited representation of a richer, more complex reality that exists beyond our immediate perception. For Plato, it was a world of ideal forms. For modern physics, it might be a two-dimensional boundary encoding information. Centuries later, the German philosopher Immanuel Kant picked up this thread and wove it into the fabric of modern philosophy with his distinction between the noumenon and the phenomenon. Kant argued that we can never truly know reality as it is in itself, which he called the noumenal world. Instead, we only ever experience the phenomenal world reality as it appears to us after being processed by the inherent structures of our own minds. Our brains come pre-equipped with categories like space, time, and causality. They are the lenses through which we view the universe, the operating system of our perception. We cannot help but see the world in terms of cause and effect, of objects located in space, because that is how our minds are built to interpret the raw data of existence. The thing in itself, the noumenon, remains forever beyond our grasp. This is a philosophical precursor to the idea that our experienced reality is a construction, a user interface generated by our neurological hardware. The holographic principle takes this a step further, proposing that not only is our perception constructed, but the very stage of space and time upon which the drama plays out is itself an emergent projection from a more fundamental layer of reality. Kant gave us the philosophy of the interface. Holography gives us a potential physics of the processor. This theme of a veiled reality is not confined to Western thought. In numerous Eastern philosophical and spiritual traditions, the world of everyday experience is described as an illusion. The Sanskrit term Maya in Hinduism refers to the powerful, divine force that creates the cosmic illusion that the phenomenal world is the only reality. The goal of spiritual practice is to see through this veil of Maya, to realize that the individual self and the perceived world of separate objects are part of a greater, unified whole, Brahman. Similarly, in Buddhism, the concept of sunyata, or emptiness, teaches that phenomena have no intrinsic, independent existence. They are empty of a separate self and are interdependent. Our suffering arises from our attachment to the illusion of a permanent, separate self and world. These traditions developed sophisticated meditative and philosophical practices aimed at directly experiencing this deeper, non-dual reality beyond the illusion of the senses. While these are primarily spiritual frameworks, their core assertion that the apparent world is not ultimate reality resonates deeply with the scientific suggestion that our three-dimensional universe is a holographic projection. It reveals a shared human intuition across cultures and centuries that there is more to existence than meets the eye. Even within the history of science itself, we can find whispers of this idea. In the 19th century, physicists were trying to understand the nature of heat and energy, leading to the development of thermodynamics. They discovered that properties like temperature and pressure were not fundamental properties of individual atoms, but emergent properties, statistical averages that only had meaning for a large collection of particles. A single molecule doesn't have a temperature. Temperature emerges from the collective dance of trillions of molecules. This was a pivotal moment, the first hard scientific evidence that the apparent properties of the world could be the result of underlying hidden processes. It set the stage for the even more radical emergence proposed by the holographic principle, where not just temperature, but space, time, and gravity themselves could be seen as collective phenomena arising from a vast network of quantum information. This long and rich history is crucial because it shows that the holographic principle is not some isolated, bizarre speculation. It is the latest, most mathematically rigorous expression of an intuition that has captivated humanity for over 2,000 years. From the shadows in Plato's cave to Kant's categories of understanding, from the concept of Maya to the emergence of temperature, the idea has been refined and reshaped, moving from pure philosophy toward testable science. Today's physicists, with their complex equations describing black hole entropy and anti-de Sitter space, are continuing this grand tradition. They are using the tools of mathematics and experimentation to explore the same fundamental question that the ancients posed: what is the true nature of reality, and how does it relate to the world we perceive? The language has changed from idealism and phenomenology to quantum field theory and general relativity, but the quest remains the same: to peek behind the curtain of appearance and glimpse the fundamental workings of the cosmos. But perhaps the most profound shift happens when we turn this lens of inquiry inward toward our own sense of self. We've journeyed through black holes and quantum codes, but what does it all mean for you and me, sitting here in this seemingly solid world? Contemplating the holographic principle isn't just an intellectual exercise. It can be a deeply personal, even emotional, experience that quietly reshapes our entire perspective on identity, purpose, and our place in the cosmos. If the rich tapestry of our reality, the feeling of the sun on your skin, the sound of a loved one's laughter, the sheer depth of the night sky is all a magnificent projection from a simpler, more fundamental layer, then what are we, the experiencers of this grand illusion? This line of thinking inevitably leads us to question the very nature of our identity. We often build our sense of self on a foundation of physical continuity. This is my body, this is my brain, this is the story of my life as a distinct individual moving through time. But if the body and the brain themselves are part of the projection, intricate patterns in the holographic display, then what is the source of the consciousness that observes it all? The you that is reading these words right now, the aware presence having this experience, might not be generated by the projection, but could be an intrinsic aspect of the process itself. It suggests that the conscious self is not a mere passenger in a mechanical body, but might be more fundamental, interacting with the projected reality from a place that exists prior to space and time. This doesn't diminish your individuality, it reframes it. Your unique perspective, your memories, your personality, they are not less real, but they might be seen as a specific, localized expression of awareness interacting with the cosmic data stream. It's a view that can feel both humbling and immensely empowering, connecting your innermost being directly to the underlying architecture of the universe. This naturally brings us to that age-old, deeply human question: what is our purpose? In a universe where physical forms are transient projections, the traditional search for purpose in material achievement or legacy can feel suddenly less anchored. But this perspective opens the door to a far more intriguing possibility. If the universe is fundamentally about information, experience, and relationship, then our purpose might be to participate in that very process. Your life, with all its complex emotions, relationships, and choices, could be a way for the universe to know itself, to experience its own creation in a rich and meaningful way. Your struggles and joys aren't meaningless events in a cold, mechanical cosmos. They are part of the data, part of the story being written on the boundary. Your purpose shifts from something you need to find out there to something you are inherently fulfilling by the very act of conscious engagement. You are not a stranger in a strange land. You are the universe, experiencing itself from a singular, precious point of view. The emotional impact of embracing this view can be a strange mix of awe and vertigo. There's a certain comfort in the solid, classical world where things are just what they appear to be. To have that foundation questioned can be unsettling, like the moment you first realized the world was round and not flat, but multiplied 1,000-fold. Yet that feeling is often followed by an incredible sense of expansion and connection. The boundaries that seem to separate us from each other and from the cosmos begin to feel more permeable. The same quantum information that projects the star billions of light years away also projects the neurons firing in your brain. We are all expressions of the same underlying reality, reading from the same cosmic source code. This can foster a profound sense of empathy and unity, a feeling that your existence is woven into the very fabric of everything, and that your journey, however small it may seem, is an integral part of the whole. It's a perspective that doesn't answer all of life's questions, but it invites us to ask them in a new, more beautiful, and deeply interconnected way. Of course, the most direct way to test such a cosmic idea would be to somehow build a universe in a lab, but since that's a tad beyond our current budget and engineering capabilities, scientists have turned to the next best thing: building digital universes inside some of the world's most powerful supercomputers. This isn't about creating a realistic video game. It's about constructing sophisticated mathematical sandboxes where researchers can literally play with the laws of physics, tweak parameters, and watch what emerges. The goal is to see if the tantalizing predictions of the holographic principle hold up in a simulated environment. Can a collection of simple, interacting parts on a flat, two-dimensional grid truly give rise to the complex behavior of a three-dimensional world, complete with something that looks and acts like gravity? These computational experiments are the crucial bridge between elegant theory and observable reality, allowing us to run experiments that nature itself might take billions of years to perform. One of the most exciting areas of this research involves simulating a specific kind of holographic universe described by the AD-S/CFT correspondence. Remember, this is the duality that says a gravitational theory in a warped five-dimensional space is equivalent to a quantum field theory on a four-dimensional flat boundary. To test this, physicists don't try to simulate the impossibly complex five-dimensional bulk directly. Instead, they start by defining a quantum system on a lower dimensional lattice, essentially a grid of points representing the boundary. They program this grid with the rules of a specific quantum field theory, one that is known to have a holographic dual. Then, they set the simulation running, allowing the quantum particles on this grid to interact, entangle, and evolve according to their programmed laws. The magic happens when the researchers then analyze the results. Using sophisticated algorithms, they look for signatures of an emergent dimension. They calculate something called the entanglement entropy between different regions of their simulated boundary. According to the theory, this entropy should follow a very specific pattern that geometrically corresponds to the properties of a higher dimensional space. It's like listening to the harmonious vibrations of a two-dimensional drumhead, and from the complex sound waves, being able to mathematically reconstruct the shape of a three-dimensional bell that would produce the same sound. And the results from these simulations have been nothing short of astonishing. In multiple studies, researchers have watched as their flat, quantum simulations spontaneously generated geometry. The calculated entanglement entropy doesn't just vaguely hint at an extra dimension. It precisely matches what you would expect from a specific curved spacetime, like the anti-de Sitter space we've discussed. In one landmark simulation, a team effectively created a tiny, digital black hole in their emergent space. They were able to watch information represented by specific patterns in their boundary quantum system fall into this simulated black hole and then, crucially, see it get scrambled and eventually re-emerge, just as the holographic principle predicts it should, resolving the information paradox in a virtual environment. This is a powerful form of validation. It shows that the mathematical dictionary of AD-S/CFT isn't just a clever analogy. It's a robust, operational principle that can be implemented and observed in a controlled computational experiment, giving us enormous confidence that the theory is on the right track. These simulations are also acting as powerful discovery tools, revealing entirely new phenomena that theorists hadn't even predicted. Because the simulations can model the quantum system on the boundary with such high precision, they can explore regimes that are too complex for our current mathematical tools to handle with pen and paper. For instance, by cranking up the interaction strength between the quantum particles on the boundary to extreme levels, researchers have observed the emergence of strange new phases of matter in the higher dimensional bulk. They've seen simulations where the emergent spacetime itself seems to undergo a phase transition, changing its geometric properties in a sudden shift, much like water freezing into ice. This suggests that spacetime might not be a fixed, static stage, but a dynamic substance that can change its fundamental nature under different conditions. Other simulations are exploring the very birth of a holographic universe, starting from a hot, chaotic state on the boundary and watching as a smooth, ordered spacetime geometry gradually cools and crystallizes out of the quantum noise, offering a digital glimpse into what a holographic Big Bang might have looked like. These virtual laboratories are not just confirming old ideas, they are actively charting new territory, guiding theorists toward deeper questions and more complete models of how reality might truly be constructed from the ground up. This incredible idea that our universe might be a projection is so mind-bending that it's no surprise it often gets tangled up with all sorts of wild interpretations and outright myths. When a concept from theoretical physics captures the public imagination, it can sometimes drift far from its scientific moorings, getting mixed with science fiction, spiritual beliefs, and even conspiracy theories. So let's take a moment to clear the air, to separate the rigorous science from the popular speculation, and get a crystal clear picture of what the holographic principle actually claims and what it definitely does not. One of the most common and persistent confusions is the belief that the holographic principle means our universe is a computer simulation, like something out of the Matrix. This is an understandable mix-up, but it's a crucial one to untangle. The simulation hypothesis is a fascinating philosophical idea. It suggests that an advanced civilization, perhaps in a higher dimension, is running our universe as a kind of sophisticated program. It's a technological speculation about who might be the programmer. The holographic principle, in stark contrast, is not about who or what is creating the universe. It is a proposed law of physics, a statement about how the universe fundamentally operates at its most basic level, with or without any outside intelligence. It says that the laws of nature themselves are structured in such a way that a description of a volume of space can be encoded on its boundary with one less dimension. Gravity and the three-dimensional world are emergent properties of this encoding. It's a statement about the architecture of reality, not its potential authorship. The simulation theory is a whodunit, the holographic principle is a how it's done. This leads to another major misconception, that if the world is a holographic projection, then it must be an illusion and therefore somehow not real. This can lead to a dangerous kind of nihilism. If nothing is real, then why does anything matter? But this misinterprets what physicists mean by emergence. Think of a whirlpool in a river. The whirlpool is not a fundamental, independent object. It emerges from the complex interactions of countless water molecules flowing together. But does that make the whirlpool an illusion? Of course not. It has real properties. It can spin a leaf around. It has a specific location and speed. It is genuinely real within the context of the river. In exactly the same way, the holographic principle suggests that our three-dimensional reality is emergent, not illusory. The chair you're sitting on is really there. It has real solidity, it obeys real physical laws, and your experience of it is completely genuine. The revelation is about its origin story, not its reality. The principle doesn't make the world less real. It reveals that the nature of its reality is far more fascinating and interconnected than we ever imagined. You might also hear the holographic principle invoked to explain paranormal phenomena, things like psychic abilities, telekinesis, or a universal consciousness. The argument goes that if the universe is a projection, then maybe our minds can somehow tap into the underlying source code and influence it with our thoughts. While this makes for compelling fiction, it is a significant leap beyond what the science actually says. The holographic principle is a specific mathematical framework within quantum gravity research. It makes precise, testable predictions about things like black hole entropy and the behavior of quantum systems. It does not provide a mechanism for bending spoons with your mind or reading someone else's thoughts. Conflating a rigorous, if speculative, physical theory with paranormal claims does a disservice to both. It waters down the science into a vague metaphor and uses the authority of physics to lend credibility to ideas that currently have no empirical support. It's essential to enjoy the wonder these ideas inspire while also respecting the clear boundary between established science, theoretical speculation, and pseudoscience. Finally, there's a notion that the holographic principle is a finished, proven theory, a settled fact of the universe. This is perhaps the most important myth to dispel for anyone who truly wants to understand the cutting edge of physics. The truth is that the holographic principle remains a highly influential but unproven hypothesis. It is a compelling framework that solves certain thorny problems, like the black hole information paradox, and it has given rise to incredibly powerful mathematical tools like the AD/CFT correspondence. But that correspondence works perfectly in a hypothetical universe with a specific geometry that is not the geometry of our observed universe. The monumental challenge of adapting it to our reality, a de Sitter space, is still very much an open area of research. Furthermore, as we've discussed, direct experimental evidence remains elusive. Scientists are hunting for it creatively, but they haven't found it yet. This doesn't make the principle worthless. This is how frontier science works. Ideas are proposed, their consequences are explored mathematically, and they are then subjected to brutal experimental testing over decades. The holographic principle is in that thrilling, precarious stage of being too beautiful to ignore but not yet proven to be true. Recognizing this uncertainty isn't a weakness. It's a testament to the integrity of the scientific process, a reminder that our understanding of the cosmos is a journey, not a destination. If the very framework of our reality is not what we have long believed it to be, what does that mean for how we ought to live within it? The holographic principle, while a scientific theory, cannot be hermetically sealed from the profound ethical questions it inevitably raises. If our world, with all its beauty and its suffering, is an emergent projection from a more fundamental layer of information, does that change the weight of our moral choices? This isn't just an abstract puzzle for philosophers. It has tangible implications for how we view suffering, our relationship with the environment, and the very nature of human agency in what might be a deeply interconnected cosmic system. Consider first the nature of physical suffering. In our traditional view, pain is an intensely local, personal event, a signal of damage to a physical body that is undeniably and fundamentally real. But if that body, that nerve ending, that injury is itself part of a projected reality, a complex pattern in a holographic display, does that make the pain any less significant? One potential and dangerous misinterpretation could lead to a form of existential nihilism. If nothing is fundamentally real in the old solid sense, one might argue, then why should we care about alleviating suffering? This is a profound ethical trap. The correct interpretation, however, points in the exact opposite direction. The suffering is no less real to the experiencer. The conscious awareness of pain is the undeniable data in the system. The holographic view, rather than diminishing suffering, could radically universalize our responsibility to address it. It suggests that every conscious being is an inseparable expression of the same underlying cosmic process. Your pain and my pain are not isolated events in separate containers. They are disturbances in a single, unified informational field. This could provide a powerful scientific underpinning for the ethical principle of compassion, framing it not as a sentimental preference but as a rational response to the interconnected nature of existence itself. We are not separate beings feeling alone. We are the universe feeling itself, and therefore to harm another is, in a very real sense, to harm a part of the whole. This leads directly to a revolutionary way of thinking about environmental ethics. For centuries, particularly in Western thought, the natural world has often been viewed as a collection of resources, separate from us, to be used for human ends. Even the modern environmental movement, while advocating for protection, often frames it as a matter of stewardship. We are the caretakers of a planet we live on. The holographic principle shatters this separation. It suggests that the mountain, the river, the atmosphere, and the human are not distinct entities interacting on a stage. They are all equally emergent phenomena, all part of the same magnificent projection from the same fundamental source. We are not on the environment, we are of it in the most literal sense possible. This isn't a vague spiritual connection, it's a potential physical reality. This perspective could forge an environmental ethic that is not based on utility or even stewardship, but on identity. Protecting an ecosystem would not be about saving something out there for future use. It would be an act of preserving the integrity of the reality we are all part of. Polluting a river wouldn't just be a bad economic or health decision. It would be a form of self-desecration, a corruption of the informational patterns that constitute our shared existence. Furthermore, this worldview forces us to re-examine the age-old debate between free will and determinism with fresh eyes. If the universe is a kind of computation, are our choices just the inevitable output of a program running its course? The answer may be more nuanced than a simple yes or no. The quantum nature of the underlying reality introduces genuine indeterminacy and probability. Our decisions might not be pre-written in a cosmic script, but could represent the collapse of possibilities at the level of our conscious interaction with the holographic display. Our sense of agency might be the experience of the universe making choices through us. This doesn't negate free will, it recontextualizes it. Our will is not that of a separate ego battling against a deterministic machine, but the expression of the universe's own inherent capacity for choice and novelty at the point of our individual consciousness. This view encourages a profound sense of responsibility. Our choices are not insignificant. They are the means by which the fundamental reality explores its own potential. Every ethical decision, every act of kindness or cruelty, becomes a data point that shapes the cosmic projection, giving our moral lives a weight and significance that is truly cosmic in scale. This breathtaking quest to understand the very architecture of reality is not the work of a lone genius in an isolated lab. It is a magnificent, sprawling symphony of global collaboration. The holographic principle, by its very nature, demands a convergence of minds from every corner of the planet and every branch of theoretical physics, because the puzzle pieces are scattered across disciplines and continents. Unifying gravity and quantum mechanics is perhaps the greatest intellectual challenge humanity has ever faced, and it's a challenge being met by a truly united nations of science, where borders blur in the shared pursuit of a deeper truth. This international effort underscores a beautiful fact. The desire to understand our universe is a universal human trait, and the tools we use are as diverse as the cultures contributing to the solution. At the forefront of this global network are the world's premier research institutes, each acting as a hub of innovation and a magnet for the brightest minds. In Europe, CERN, the European Organization for Nuclear Research, is famous for its particle colliders, but its influence extends far beyond smashing protons. The theoretical physics departments there are hotbeds for exploring the implications of holography, particularly through the study of quark-gluon plasmas. This state of matter, created in heavy ion collisions, behaves like a nearly perfect fluid, and its properties can be described using the mathematical tools of the AD/CFT correspondence. It's a stunning example of how a giant machine designed for one purpose can provide crucial insights for a completely different, seemingly abstract theory. Across the Atlantic, the Institute for Advanced Study in Princeton, New Jersey, carries on the legacy of Einstein with a relentless focus on fundamental questions. It was here that Juan Maldacena, now a professor, developed his groundbreaking AD/CFT correspondence, and the Institute continues to be a central meeting point for theorists working on quantum gravity and holography, fostering the kind of deep, unstructured thinking that leads to true revolutions. The collaboration extends powerfully across the Pacific. In Japan, the Yukawa Institute for Theoretical Physics at Kyoto University has been a cornerstone of theoretical physics for decades, with a particularly strong tradition in string theory and its holographic applications. Chinese institutions like Tsinghua University in Beijing are rapidly expanding their efforts in this area, investing heavily in both theoretical research and the computational power needed to run complex simulations. India, with its rich history in mathematics and theoretical physics, contributes profound insights from institutes like the Tata Institute of Fundamental Research and the International Center for Theoretical Sciences in Bangalore. This isn't a competition, it's a constant, vibrant exchange. A postdoctoral researcher from Italy might spend a year at a lab in California, working with a team that includes scientists from India and Brazil, before presenting their findings at a workshop in Japan. The flow of people and ideas is the lifeblood of the field, ensuring that no single perspective dominates and that breakthroughs can come from anywhere. The glue that binds this global community together is the constant rhythm of conferences and workshops. These are not dry, formal affairs, but the dynamic engines of scientific progress. Events like the Strings Conference, which moves to a different international city each year, or specialized workshops on topics like quantum information in quantum gravity, held at places like the Kavli Institute for Theoretical Physics in Santa Barbara, are where the real magic happens. It's in the lecture halls, over coffee breaks, and during late-night discussions that a casual comment from a colleague can resolve a months-long calculation block, or where a presentation on a new mathematical technique can open up an entirely new research direction for a dozen different groups at once. These gatherings are where a young graduate student can present a bold idea to the very pioneers who wrote the textbooks they study, creating a living, breathing scientific tradition that constantly renews itself. The shared language is mathematics, and the common goal is a unified understanding, making these events a powerful testament to how science can transcend politics and culture in the pursuit of pure knowledge. This spirit of collaboration is now being supercharged by the digital age. The Internet has transformed theoretical physics into a truly real-time, global conversation. Preprint servers like RZIV.org allow a researcher in Moscow to upload a new paper at night and have it be read, dissected, and built upon by a team in Tokyo by the next morning. Online seminars and virtual collaboration tools have demolished the remaining barriers of geography and travel costs, allowing for instant feedback and continuous partnership across oceans. Large-scale collaborative projects, often involving dozens of scientists from a dozen different countries, are now the norm for tackling the biggest problems. They might be using supercomputers in Germany to run simulations based on equations developed in Canada to test a conjecture first proposed in Argentina. This seamless worldwide web of intellect is a powerful force, accelerating progress and ensuring that the investigation into the holographic nature of our universe is the most collaborative and interconnected scientific endeavor in history. But to truly grasp how this dimensional trick works, we need to understand the mysterious quantum phenomenon that acts as its fundamental building block, quantum entanglement. This bizarre connection, which Einstein famously called spooky action at a distance, is far more than just a curious feature of the subatomic world. Within the framework of the holographic principle, entanglement isn't a side effect. It is the very glue that holds the projected universe together, the invisible thread stitching the fabric of spacetime into a cohesive whole. Imagine two particles born from the same quantum event, instantly linked in such a way that measuring the property of one, say, its spin instantaneously determines the property of the other, no matter how far apart they are separated. This isn't a signal traveling faster than light. It's a deeper connection that seems to defy our classical notions of locality and separateness. Now, scale that idea up from two particles to an almost unimaginable number. Picture the entire two-dimensional boundary of our universe as a vast, seething ocean of quantum information, with every single bit entangled with countless others in an impossibly complex web. According to the holographic principle, this web of entanglement is what literally weaves together the higher dimensional reality we experience. Every connection between bits on the boundary creates a kind of quantum bridge, and the collective strength and pattern of these billions upon billions of bridges is what generates the geometry of the three-dimensional space projecting from that surface. The distance between 2 points in our world isn't a fundamental property. It's an emergent one, determined by how deeply entangled the corresponding bits of information are on the boundary. The more entangled they are, the closer they appear in the projected reality. This profound link is quantified by a concept known as entanglement entropy. In simple terms, this is a measure of the quantum information shared between two systems. For any given region of space, you can calculate how entangled it is with everything else. The stunning revelation from holography is that this purely quantum mechanical calculation of entanglement entropy is directly proportional to the area of the surface that separates that region from the rest of the universe. This is a precise mathematical restatement of Bekenstein's area law entropy for black holes, but it now applies to any region of space. It's as if the universe has a fundamental resolution limit, and that limit is set by the density of the informational glue, the entanglement that binds it. The more entangled a system is, the more information it shares with its surroundings, and the more vividly and solidly it projects into the emergent spatial dimensions. This provides an elegant answer to a question we posed much earlier. How does a smooth, continuous spacetime emerge from a discrete quantum boundary? The answer lies in the density of this entanglement. If the quantum bits on the two-dimensional surface are only entangled with their immediate neighbors, the resulting projected spacetime is highly fragmented and disconnected, like a poorly rendered digital image with visible pixels. But if the entanglement is vast, deep, and complex, with each bit connected to many others across the entire network, the resulting projection becomes smooth, continuous, and coherent. The seamless classical reality we move through every day. The force of gravity itself may be a manifestation of this underlying quantum entanglement, a thermodynamic force that arises from the universe's innate tendency to maximize its connectivity and disorder. In this view, the holographic principle reveals a universe that is not built from tiny, solid balls of matter, but from relationships. It is a cosmic tapestry where the threads are quantum connections, and the magnificent, three-dimensional image that emerges is a testament to the profound power of information and interconnection. This breathtaking scientific idea that our reality might be a magnificent projection from a simpler, lower-dimensional source doesn't just live in the rarefied air of theoretical physics. It has spilled over into the vibrant world of art, where creators are using it as a profound source of inspiration. Artists, in their quest to explore the nature of perception and existence, are building bridges of intuition between complex equations and human experience. They are crafting visual and sensory poems that attempt to translate the holographic principle from a mathematical concept into something we can feel in our bones, giving form to the formless and making the abstract tangibly wondrous. In the realm of digital art, this has led to some truly stunning creations that directly play with the idea of dimensions and emergence. Consider the work of artists who use generative algorithms and complex data visualizations. They might start with a flat, two-dimensional grid of points, a direct analog to the theoretical boundary. Then, they code relationships between these points, rules for connection and interaction that mirror the quantum entanglement of the holographic model. As the algorithm runs, a three-dimensional shape begins to bloom from the flat screen, its form entirely determined by the coded relationships on the underlying grid. The artist isn't sculpting the final form. They are designing the rules of engagement on the lower dimensional surface and watching as a higher dimensional reality emerges, perfectly illustrating the core concept that complexity and dimension are born from simple relational rules. Viewers can watch a swirling galaxy of light and color coalesce from a flat, seemingly random network of lines, a silent, beautiful testament to the idea that our universe might arise in much the same way. Sculptors, too, are grappling with these ideas, facing the unique challenge of representing multidimensional spaces in a stubbornly three-dimensional world. Some create intricate, layered pieces that suggest a higher dimension folded into our own. Imagine a sculpture made of countless thin, laser-cut sheets of metal or acrylic, each etched with a complex two-dimensional pattern. When viewed from the front, these stacked sheets resolve into a single, solid-looking three-dimensional object, like a human head or a geometric form. But as you walk around it, the illusion breaks. You see the gaps between the sheets, the individual layers. The sculpture exists simultaneously as a collection of independent two-dimensional planes and as a unified three-dimensional whole, powerfully embodying the holographic notion that a solid reality can be an emergent property of information stored on separate, lower-dimensional surfaces. It's a physical metaphor you can walk around and touch, making the abstract theory feel immediate and concrete. Filmmakers and creators of immersive, virtual reality experiences are perhaps in the strongest position to make us feel what a holographic universe might be like. They can literally construct a reality for us to step into. In VR, an artist can create a world that appears vast, three-dimensional, and fully explorable. Yet the entire experience is being rendered in real time from code, from a set of instructions on a two-dimensional computer chip. As you don a headset and reach out to touch a virtual flower, your brain is completely convinced of its reality. Yet you know intellectually that the flower is not there. It is a projection, a pattern of light generated from underlying data. This is the closest many of us will ever come to experiencing the central question of the holographic principle firsthand. Are we the user in the headset, blissfully unaware of the code that creates our world? These artistic experiences don't provide answers, but they masterfully evoke the eerie, exhilarating sensation that the nature of reality is far stranger than it appears, transforming us from passive listeners to active participants in a philosophical inquiry. Ultimately, the power of this artistic interpretation is not about providing a technically accurate model of anti-de Sitter space. It's about communication and evocation. Science gives us the equations and the evidence, but art gives us the wonder. It translates the chilling beauty of a black hole's entropy into a visual symphony that resonates on an emotional level. It takes a concept that could feel alienatingly complex and makes it accessible, allowing a broader audience to grapple with its implications. A person who might never understand the mathematics of the AD/CFT correspondence can stand before a sculpture that embodies its principles and have a sudden, intuitive flash of understanding. They can feel the concept. In doing so, these artists become vital partners in the scientific endeavor. They are not just illustrating ideas, they are expanding the conversation, reminding us that the quest to understand the universe is not just a technical challenge but a deeply human one, driven by awe and a desire to find our place within the grand and possibly holographic scheme of things. Yet as we stand at this fascinating crossroads, it's crucial to navigate this dialogue with both respect and clarity. The goal is not to claim that ancient mystics discovered the AD/CFT correspondence, nor to assert that modern physics is simply validating age-old beliefs. Rather, it's to recognize that both science and spirituality, in their own distinct ways, are human responses to the profound mystery of existence. They use different languages and different methods. One employs mathematics and empirical testing, the other employs meditation and philosophical inquiry, but they can sometimes arrive at strangely consonant insights about the nature of reality. This doesn't mean they are saying the same thing, but that they are exploring the same vast territory from different trails. The value of this conversation lies not in conflating these distinct domains, but in allowing them to inform and perhaps even deepen each other. Physics can offer a potential mechanistic framework for how reality might be structured, while spiritual traditions can offer a lived, experiential dimension of what it might mean to perceive that reality directly, beyond the veil of the conceptual mind. This enriches our understanding by reminding us that the cosmos is not just a puzzle to be solved, but an experience to be lived, a mystery that engages not only our intellect but our entire being. It suggests that the ultimate nature of reality might be something that can be approached through both calculation and contemplation, and that both paths, in their own way, are valid and valuable human endeavors. Wrapping our minds around a holographic universe is perhaps one of the greatest feats of imagination physics has ever asked of us. Our brains, after all, are exquisitely tuned by millions of years of evolution to navigate a world of 3 spatial dimensions. We intuitively understand depth, volume, and perspective. We can judge the trajectory of a thrown ball or navigate a crowded room without a second thought. This hardwired perception makes the very idea that all of this richness could be encoded on a flat, 2-dimensional surface feel not just counterintuitive, but almost impossible. How can the vast, star-filled expanse of the night sky, the solid mountain range on the horizon, and the intricate dance of subatomic particles all be contained on a cosmic screen with no thickness at all? The challenge isn't just intellectual, it's perceptual. We are, in a sense, like the characters in Edwin Abbott's Flatland, struggling to conceive of a reality that operates in a dimension beyond our innate sensory experience. So how do we bridge this gap? How do we train our 3D-wired brains to at least glimpse the possibility of this dimensional trick? We start by leaning on the power of analogy, finding familiar concepts that can act as stepping stones into this unfamiliar territory. One of the oldest and most effective analogies is Plato's allegory of the cave, which we touched on earlier. Imagine prisoners chained in a cave their entire lives, facing a blank wall. Behind them, a fire burns, and people walk between the fire and the prisoners, carrying objects that cast shadows on the wall. For these prisoners, those two-dimensional shadows are the entirety of reality. They have no concept of the three-dimensional objects and the fire that are the true sources of the shapes they see. In this analogy, we are the prisoners. Our seemingly 3D world of atoms, forces, and galaxies could be the shadow play, while the true fire and objects are the fundamental quantum information interacting on the distant two-dimensional boundary. It's not a perfect one-to-one comparison, but it powerfully captures the core idea that our perceived reality might be a superficial representation of a deeper, more fundamental process. A more modern and technologically relatable analogy is that of a hologram itself. Look at the security hologram on your credit card or passport. It's a flat, shiny sticker. But when you tilt it under the light, a stunningly realistic three-dimensional image seems to pop out, with depth and parallax that changes as you move your head. The key here is that the entire 3D image isn't actually stored in the sticker in the way a sculpture is stored in a block of marble. Instead, the flat surface is etched with an incredibly complex pattern of microscopic grooves that diffract light in just the right way to reconstruct the image in your eye and brain. All the information needed to create the convincing illusion of three dimensions is contained on that two-dimensional surface. The holographic principle suggests our universe operates on a similar, though infinitely more complex, principle. The entire cosmic data set, every particle, every force, the entire history of everything, could be etched into the fundamental fabric of a two-dimensional boundary. And what we experience is the magnificent projection, the cosmic light show reconstructed for us to perceive and inhabit. For those who want to go beyond analogies and get a more concrete, hands-on sense of how this encoding might work, there are incredible digital tools available. Physicists themselves use sophisticated software and simulations to visualize these concepts. For instance, there are interactive online simulations that model tensor networks, those webs of interconnected nodes we discussed. You can literally manipulate the strength of connections between nodes on a two-dimensional grid and watch as the software calculates and displays the emergent three-dimensional geometry that this network describes. It's a profound experience to see with your own eyes how changing relationships on a flat plane can literally generate depth, curvature, and volume. Other programs visualize the anti-de Sitter space and its boundary, allowing you to fly through this hyperbolic geometry and see how a light beam traveling in the bulk can be mapped to a point propagating on the boundary. These tools are not just for experts. They are becoming increasingly accessible, offering anyone with curiosity a window into the mathematical machinery that might underpin our reality. They transform the holographic principle from a baffling abstraction into a dynamic, almost tactile process that you can explore and interrogate. Ultimately, the goal isn't to achieve a perfect mental picture. That might be impossible with our current cognitive apparatus. The goal is to develop a new kind of intuition, a fluency with the language of emergence and information. It's about accepting that the solidity of the world is a kind of necessary and consistent user interface for conscious beings like us, while being open to the staggering possibility that the source code of that interface is written in a simpler, lower-dimensional language. By combining ancient philosophical allegories with modern technological visualizations, we can stretch the limits of our perception and begin to truly appreciate the elegant and perhaps holographic architecture of the cosmos we call home. But what is the secret ingredient that makes this incredible translation between dimensions not just possible, but mathematically elegant and robust? The answer lies in a concept that has guided physicists toward deeper truths for over a century: symmetry. In the holographic universe, symmetry isn't just a pleasant aesthetic. It is the fundamental engine that drives the entire correspondence, the precise geometric language that allows a quantum theory without gravity on a flat boundary to speak perfectly to a gravitational theory in a curved, higher dimensional bulk. It is the hidden harmony that makes the dimensional trick not a messy hack, but a thing of breathtaking beauty and power. To understand this, we first need to appreciate what physicists mean by symmetry. We often think of symmetry in visual terms, like the mirrored wings of a butterfly or the perfect radial petals of a flower. In physics, symmetry is a much deeper idea. It is a transformation that leaves the underlying laws of a system unchanged. Imagine rotating a perfect, featureless sphere. No matter how you turn it, it looks exactly the same. The sphere is said to be symmetric under rotation because its appearance, and more importantly, the physical laws describing it, don't change with the rotation. Now apply this to the very laws of physics themselves. A theory has symmetry if you can change your perspective, say, move to a different location, rotate your view, or even travel forward in time. And the fundamental equations describing how particles interact and forces operate remain identical. This requirement of symmetry is an incredibly powerful constraint. It forces the laws of physics to take on very specific and often very beautiful mathematical forms. In many ways, the history of modern physics is the story of discovering ever more profound symmetries lurking within the machinery of the universe. In the specific case of the AD/CFT correspondence, the magic is made possible by a very special and powerful type of symmetry called conformal symmetry. This is the C in CFT, or conformal field theory, which lives on the lower dimensional boundary. Conformal symmetry is more flexible than the rigid symmetries of rotation or reflection. Imagine taking a detailed map and enlarging it uniformly. The distances between cities change, but the angles at which the roads intersect remain exactly the same. A theory with conformal symmetry is invariant under these kinds of scale transformations, zooming in and out as well as certain other distortions. It means the physics looks the same at all scales. There is no built-in meter stick or fundamental length. This scale invariance makes conformal field theories particularly mathematically tractable and powerful. The quantum dance of particles on the boundary doesn't care if you're looking at it from up close or far away. The patterns of their interactions remain consistent. Now shift your perspective to the higher dimensional bulk, the de Sitter space where gravity holds sway. This curved universe has its own set of majestic symmetries, governed by the rules of Einstein's general relativity. The key here is that the specific hyperbolic curvature of de Sitter space is precisely the kind of geometry that naturally admits a set of gravitational symmetries. And here is the breathtaking part: the catalogue of symmetries in the gravitational bulk and the catalogue of symmetries in the conformal field theory on the boundary are mathematically identical. They are two different manifestations of the same underlying symmetrical structure. The conformal symmetry on the boundary is the perfect mirror image reflection of the gravitational symmetry in the bulk. This shared symmetry is the Rosetta Stone that allows for a perfect dictionary between the two worlds. It guarantees that for every symmetrical transformation you can perform on the quantum particles living on the boundary, there is a corresponding, equivalent transformation warping the geometry of the gravitational bulk, and vice versa. This profound connection does far more than just make the mathematics consistent. It actively simplifies it in ways that feel almost miraculous. Problems that are notoriously difficult to solve in one description often become astonishingly straightforward when translated into the other language using this symmetrical dictionary. A physicist struggling to calculate the immensely complex interactions of a dense soup of quarks and gluons in the quantum boundary theory might find that the problem translates into a much simpler calculation involving the motion of a single particle or the geometry of a black hole in the gravitational bulk. The symmetry acts as a guiding light, revealing shortcuts and simplifications that were completely invisible from within a single description. It's as if you were trying to navigate a vast, complex maze, and someone handed you a map drawn from a higher vantage point, making the path suddenly obvious. This is why the holographic principle is more than just a curious duality. It is an incredibly powerful computational tool, and that power is derived directly from the unifying language of symmetry. Ultimately, this points toward a deeper truth about the universe that symmetry has always hinted at, a fundamental unity beneath apparent complexity. The holographic principle, through its symmetrical foundation, suggests that the frantic, probabilistic world of quantum particles and the smooth, geometric curvature of spacetime are not two separate, conflicting realities. They are two different ways of looking at a single, unified whole. The symmetry is the bridge between them, proving that they are mathematically equivalent descriptions of the same underlying truth. This revelation guides physicists toward future discoveries, suggesting that the ultimate theory of quantum gravity will not be found by forcing quantum mechanics onto gravity's stage, but by identifying the deeper, symmetrical principles from which both emerge naturally. The role of symmetry in holography is a powerful reminder that the universe, in all its bewildering complexity, seems to operate on principles of elegance and economy, using the language of mathematics and geometry to reveal a hidden order that connects every dimension of existence. As our exploration of this extraordinary idea draws to a close, we're left standing at the edge of a new frontier in human understanding. The journey we've taken together, from the event horizons of black holes to the quantum-entangled threads that may weave the very fabric of spacetime, reveals a universe far stranger and more magnificent than we could have imagined. The holographic principle doesn't just offer a new set of equations. It invites us into a completely new way of seeing, where the rich, three-dimensional reality we experience might be the grandest emergent story ever told, projected from a simpler, more fundamental realm operating in fewer dimensions. This isn't merely a technical adjustment to physics. It's a profound shift in perspective that touches on everything from the nature of consciousness to our deepest questions about meaning and connection. What makes this vision so compelling is its breathtaking elegance. The notion that the cosmos might achieve its magnificent complexity through a kind of dimensional economy, that the laws governing galaxies and subatomic particles could be unified on a distant, lower dimensional surface, suggests a universe that operates on principles of stunning simplicity beneath its apparent chaos. This doesn't diminish the wonder we feel when gazing at the stars. It amplifies it, revealing a hidden order and interconnectedness that binds every part of existence together. The force of gravity, the passage of time, the very stage of space itself, all might be part of an immersive, consistent illusion generated by the cosmic processing of information. This realization encourages a profound humility, reminding us that our perception, while powerful, reveals only a fraction of the deeper truth. Yet for all its promise, the holographic principle remains a vibrant, open field of inquiry, not a settled dogma. The most exciting aspect of this journey is that it's far from over. The questions that remain are as thrilling as the answers we've begun to uncover. How can we adapt these ideas to our own accelerating, de Sitter-like universe? What experimental signatures might finally provide conclusive evidence? How does consciousness fit into this informational picture of reality? These are the puzzles that will drive the next generation of physicists, philosophers, and perhaps even artists and poets, as we continue to unravel the mysteries of existence. This ongoing quest demonstrates the beautiful, self-correcting nature of science, a process of constant wonder, rigorous debate, and relentless curiosity. Ultimately, the greatest gift of this exploration may be the way it rekindles our sense of awe and reconnects us to the cosmos. The holographic principle suggests that we are not passive observers in a cold, mechanical universe, but active participants in a reality that is, at its heart, relational and informational. Your consciousness, your experiences, your very sense of self, all are woven into the fundamental fabric of everything. This perspective fosters a deep sense of kinship with the universe and with each other, reminding us that we are all expressions of the same underlying reality, reading from the same cosmic source code. As you go about your day, remember that the solid world around you is both genuinely real and potentially emergent, a testament to the universe's incredible capacity for creativity and connection. Thank you for joining this mind-expanding journey. We can't wait to continue exploring the mysteries of existence with you.